What if the universe didn't begin with something, but with nothing at all? No space, no time, no matter, just nothing. That idea might sound more like a riddle than science. Yet it sits at the heart of one of the most profound questions in modern cosmology. How did the universe begin if there was truly nothing before it? What does nothing even mean in a scientific sense? Is it an empty void, a quantum field, or something beyond the reach of language and physics? To ask what came before the Big Bang is not just a question about the past, it's a challenge to the very structure of reality itself. What does it mean for something to come from nothing? It is a question that sounds almost absurd, like a contradiction built into language itself. And yet, when we ask how the universe began, we are really asking just that. Not merely how stars and galaxies formed, or even how space and time expanded. But what, if anything, was there before? Could the universe have emerged from absolute nothingness? Or does that idea collapse under scientific scrutiny? For much of history, this was not a question for physicists. It belonged to philosophers and theologians who debated whether there could ever be a true void, a total absence of existence. But as science advanced, particularly through cosmology and quantum physics, the boundaries between philosophical speculation and empirical investigation began to blur. Today, cosmologists explore conditions so extreme, so close to the edge of the knowable, that the question of nothing has re-entered scientific discourse with renewed urgency. In our daily experience, nothing is a relative term. We might say a room is empty or a box contains nothing. But of course, these spaces still contain air, radiation, gravity, and the subtle structures of space-time. Even the vacuum of outer space is not truly empty. It is filled with fields, particles, and fluctuations invisible to the eye. So when physicists refer to nothing, they must be much more precise and far more cautious. The modern scientific paradox of nothing began to take shape in the early 20th century, a time of extraordinary upheaval in physics. In the year 1915, Albert Einstein introduced his general theory of relativity, redefining gravity not as a force, but as the curvature of space-time. Space and time were no longer static, empty stages on which events unfolded. They were now dynamic participants in the drama of the cosmos, shaped by energy and mass. This insight would soon lead to a deeper realization. If space and time could bend, stretch, or compress, perhaps they could also begin or end. Just over a decade later, in the late 1920s, astronomer Edwin Hubble made a startling discovery at the Mount Wilson Observatory in California. By measuring the redshift of distant galaxies, he found that they were all moving away from us. The universe, it seemed, was expanding. This finding upended the prevailing belief in a static cosmos and pointed backward in time to a more compact, hotter, denser state. If the universe was expanding now, then logically it must have been smaller in the past. Much smaller, possibly small enough to emerge from a single point. This idea became the foundation for what is now known as the Big Bang theory. But the theory raised as many questions as it answered. What caused the expansion? What came before it? And crucially, did time itself have a beginning at that moment? If so, can we meaningfully speak of a before at all? These questions were not immediately addressed in the early models of the Big Bang. For a time, they were set aside as unknowable or simply irrelevant. After all, without evidence or observable consequences, speculation about before the Big Bang seemed unscientific. But over time, advances in physics, particularly quantum mechanics, began to open new possibilities. Quantum theory, developed through the work of Max Planck, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and many others between the early 1900s and mid-century, revealed that even in a vacuum, particles and energy could spontaneously fluctuate into existence. Empty space, it turned out, was not truly empty. It had structure, it had laws, and it had potential. This realization challenged older notions of nothingness. If a vacuum could give rise to particles, could it also give rise to space and time themselves? Could the entire universe have emerged as a quantum event, perhaps the ultimate fluctuation? The physicist Edward Tryon made this suggestion in the early 1970s, proposing that the universe might be a quantum fluctuation of the vacuum. At the time, the idea was considered radical, but as quantum field theory and cosmological models advanced, the idea began to gain traction. The discovery of cosmic microwave background radiation in the mid-1960s by Arno Penzias and Robert Wilson at Bell Labs gave strong support to the Big Bang model, and the observed flatness and uniformity of the universe raised new questions about how the early cosmos had evolved so smoothly. In response to these puzzles, inflationary theory was proposed in the early 1980s by Alan Guth, followed by contributions from Andre Linde and others. Inflation posited that the universe underwent a brief but enormous expansion in a fraction of a second after the Big Bang. This idea helped explain several features of the observable universe, but it also raised new questions about initial conditions. What triggered inflation? What state existed before it began? By this point, physicists were forced to confront the idea that nothing might not mean an empty void, but a special kind of physical state, one governed by laws, symmetries, and possibilities. This idea is subtle but critical. In the classical sense, nothing implies the absence of everything: no space, no time, no energy, no laws. But in physics, even the most stripped-down state, what some call a quantum vacuum, still has rules. It is not truly nothing in the absolute sense. Here lies the paradox. If our universe arose from nothing, then that nothing must have had some properties, some capacity to generate, fluctuate, or evolve. But if it had such properties, can it still be called nothing? Or is it simply a special kind of something, perhaps the simplest, most symmetrical something conceivable? Physicist and author Lawrence Krauss explored this in his book, A Universe from Nothing, arguing that modern physics allows for a naturalistic origin of the cosmos from quantum principles. But critics, including philosopher David Albert, pointed out that Krauss's nothing still contained fields, laws, and mathematical structure. In that sense, it was far from the philosophical void that many associate with the word. This debate reflects a deeper tension between language and physics. Our words, nothing, space, time, cause, evolved for everyday use, not for describing the origins of the cosmos. When physicists push theories to their extremes, they often find that language breaks down and new concepts must be invented. This is especially true when dealing with the earliest moments of the universe, or conditions where classical intuitions no longer apply. To navigate this, physicists have turned increasingly to mathematics. Equations do not suffer from semantic ambiguity. They describe relationships, not meanings. Yet even in mathematics, certain questions remain open. General relativity breaks down at the singularity of the Big Bang, where density and curvature become infinite. Quantum mechanics, on the other hand, does not yet provide a complete theory of gravity. A unified theory, such as quantum gravity or string theory, may one day resolve this. But for now, we remain suspended between two powerful frameworks, each of which illuminates part of the mystery. Despite these gaps, cosmologists have made remarkable progress in mapping the early universe. Satellite missions such as COBE, WMAP, and Planck have measured the cosmic microwave background with exquisite precision, giving us a detailed picture of the universe less than 400,000 years after its origin. Particle accelerators like the Large Hadron Collider probe the properties of matter at energies close to those of the early universe. And advanced telescopes scan deep into space, capturing light from billions of years ago. All of these tools bring us closer to understanding the conditions that gave rise to space, time, and matter. But they also sharpen the question, if the universe has a beginning, what does that mean for the concept of nothing? And if time itself began at the Big Bang, can we ever know what, if anything, preceded it? This is the paradox that lies at the heart of our story. To understand how the universe could arise from nothing, we must first understand how earlier thinkers, scientists, and philosophers alike defined that term and how their definitions evolved over time. Only then can we begin to trace the path that leads from ancient ideas of the void to the frontier models of modern cosmology. But long before physicists attempted to model the early universe, long before quantum theory or cosmic background radiation, humans had already begun asking what might lie beyond the visible world. The idea of nothing is not a modern invention. It stretches deep into antiquity, where philosophers and mystics struggled with the same fundamental mystery. How can something come from nothing? And what even is nothing to begin with? In the ancient world, the very idea of nothingness was not only perplexing, it was controversial. Many early thinkers outright rejected the possibility that true nothingness could exist. Among them was the Greek philosopher Parmenides, writing in the 5th century before the Common Era. In one of the earliest metaphysical arguments ever recorded, Parmenides insisted that nothing could not be thought, because to think of something is already to make it exist in some way. Therefore, he argued, nothing does not exist and cannot exist. The void, in this view, is an illusion, a failure of logic or perception. This may sound abstract, but it had real consequences for early science and philosophy. If nothingness was impossible, then motion and change also became suspect. After all, how could an object move from one place to another unless there were empty space to receive it? Parmenides' strict logic led to a static, unchanging world, a radical idea even by ancient standards. It was the atomists who offered the first major challenge to this view. In the 5th century before the Common Era, Leucippus and his student Democritus proposed a bold idea. All matter is made of indivisible units called atoms, moving through a background of empty space. This void, kenon in Greek, was essential to their model. Without it, atoms could not move, collide, or form the visible world. For the atomists, nothingness was not only real, it was necessary. It was the arena in which existence unfolded. This concept marked one of the earliest attempts to link the visible and invisible, to explain the structure of reality by positing a background that could not be seen but must be there. It was a stunning intellectual leap, and one that foreshadowed later scientific efforts to describe the vacuum, the ether, and eventually space-time itself. Yet the idea of a void remained controversial. Plato, writing in the 4th century before the Common Era, was skeptical of atomism and of the void. In his dialogue Timaeus, he offered a cosmology based not on particles and emptiness, but on ideal forms, mathematical harmony, and a divine craftsman shaping the cosmos. Aristotle, his student, took a more systematic approach and devoted considerable attention to the question of the void. Aristotle rejected the existence of a true vacuum. In his view, nature abhorred a vacuum, a phrase later paraphrased in Latin as natura abhorret a vacuo. He believed that all space was filled with substance, whether air, fire, water, or other elements. For Aristotle, space could not exist independently of the things within it. There was no such thing as empty space, only regions filled with different forms of matter. This view dominated scientific thought for centuries. Aristotle's authority, reinforced by the teachings of the Catholic Church in medieval Europe, helped enshrine the idea that the universe was full, structured, purposeful, and complete. Even as science began to question Aristotelian physics, the rejection of the void remained influential. In the Roman era, the poet and philosopher Lucretius helped preserve the atomist view in his long poem De Rerum Natura, on the nature of things. Drawing from Democritus and Epicurus, Lucretius described a universe composed of atoms in constant motion through infinite void. He used vivid language and metaphor to make abstract ideas accessible, hoping to free readers from superstition and fear of the gods. Though largely ignored in his time, Lucretius' work would be rediscovered during the Renaissance, playing a crucial role in the revival of scientific curiosity. Meanwhile, in India, Jain philosophers also grappled with the concept of emptiness. Jain cosmology distinguished between akasha, or space, and alokakasha, the space beyond the universe, an infinite, empty region that does not interact with matter or time. Though not identical to the Western void, this concept revealed a similar effort to reason about boundaries, absence, and the limits of existence. Buddhist thinkers, especially in Mahayana traditions, took a different route. Rather than focusing on physical nothingness, they explored the idea of shunyata, emptiness, as a metaphysical principle. This did not mean the absence of matter, but the absence of fixed essence in all things. Everything, they taught, is interdependent and impermanent. From this perspective, even the question of what came before is a product of mistaken perception. Reality is not built from enduring substances emerging from a void, but from ever-changing processes without a fixed beginning. By the early centuries of the Common Era, thinkers across the ancient world were wrestling with the tension between form and emptiness, being and non-being. In the Islamic Golden Age, philosophers like Al-Farabi and Avicenna inherited Greek thought and began to reconcile it with monotheistic theology. The question of creation from nothing, creatio ex nihilo, became central to debates about God, time, and causality. This theological concept, creation from nothing, marked a significant turn in the Western understanding of origins. In the Judeo-Christian tradition, particularly as it evolved through late antiquity and the Middle Ages, the dominant view was that God created the universe not from pre-existing materials, but from absolute nothingness. This was not a scientific hypothesis, but a theological commitment that the universe had a beginning and that its origin was a divine act beyond natural explanation. By the time of Augustine of Hippo in the 4th and 5th centuries, the notion of time itself was being questioned. Augustine famously wrote in Confessions that time began with creation and that it made no sense to ask what God was doing before time began, since time itself is part of creation. This idea, remarkably, anticipated some of the problems that would arise in modern physics. If time has a beginning, then causality, our sense of one thing leading to another, may not apply in the way we intuitively expect. Throughout the medieval period, philosophical and religious discussions about the void continued. Scholars debated whether God could create a vacuum, whether angels could occupy empty space, and whether divine power was limited by the structure of reality. These may sound like abstract puzzles, but they helped sharpen the conceptual tools that would later be applied to physics. The distinction between logical possibility, physical law, and divine will became part of a growing intellectual framework. As Europe entered the Renaissance, ancient texts were rediscovered, translated, and debated. The atomists returned to the stage. So did questions about the void. The invention of the telescope and microscope opened new windows into worlds previously unseen. Slowly, the authority of Aristotle began to wane, making space for new ideas to emerge. By the 17th century, these debates would enter a new phase, one grounded not in metaphysics, but in experiment and observation. Galileo Galilei would observe the moons of Jupiter and the craters of the moon, challenging the perfection of the heavens. Evangelista Torricelli, a student of Galileo, would create a partial vacuum in a glass tube, paving the way for the barometer. And Isaac Newton, with his laws of motion and gravity, would envision a universe filled with invisible forces, but also structured by absolute space and time. The story of nothing was about to take a decisive turn. No longer merely a subject for philosophical musing or religious doctrine, it would become a measurable, testable, and deeply puzzling feature of the physical world. In the centuries to come, scientists would explore whether the void was real, whether space could exist without matter, and whether time itself might have a beginning or an end. As the Renaissance gave way to the scientific revolution, the questions once framed in terms of void and substance began to take on new mathematical precision. Philosophers were now becoming natural philosophers, early scientists, who sought to describe the world not through metaphysical principles, but through laws grounded in observation and reason. And no figure did more to crystallize this shift than Isaac Newton. Continuing the thread from the rediscovery of atomism and the experimental probing of vacuums, Newton's work marked a turning point in how thinkers conceived of space, time, and ultimately the fabric of the universe. He took up the question of whether space could exist in the absence of matter and whether time could flow without events. His answer, delivered through a groundbreaking synthesis of physics and mathematics, was both elegant and bold. Space and time are absolute. They exist independently of anything within them. Newton was born in the year 1642 in Woolsthorpe, England, the same year Galileo Galilei died. By the time he published his Philosophia Naturalis Principia Mathematica, commonly known as the Principia, in the year 1687, he had transformed the foundations of science. Within its pages, Newton formulated his three laws of motion and his law of universal gravitation. But perhaps even more influential than the equations themselves was the framework in which they operated. In Newton's universe, space was an infinite, fixed, three-dimensional stage, unchanging and eternal. It was not filled with ether or divine presence. it was simply there. Time, too, was absolute, flowing uniformly and without reference to anything external. These ideas were not just philosophical, they were built into Newton's physics. His laws of motion assumed that you could measure velocity, acceleration, and force against an invisible, unchanging background. Space and time were like the grid lines of a cosmic map, essential but not dependent on what was drawn upon them. This notion allowed Newton to calculate the orbits of planets, the paths of comets, and the behavior of projectiles with unprecedented accuracy. It provided a powerful, predictive framework that made sense of both celestial and terrestrial motion, and it gave a coherent picture of the cosmos that could be extended infinitely in all directions, both in space and in time. Yet Newton was not unaware of the philosophical implications of his ideas. He recognized that treating space and time as real entities, things that existed even when empty, might raise questions. In correspondence with the theologian and philosopher Samuel Clarke, Newton defended his concept of absolute space as a reflection of God's omnipresence. For Newton, space and time were expressions of divine attributes, infinite, eternal, and uniform. They were not created things, but conditions through which creation unfolded. Still, not all of Newton's contemporaries agreed. The German philosopher Gottfried Wilhelm Leibniz, who famously disputed Newton's priority in developing calculus, also rejected the idea of absolute space. Leibniz argued for a relational view. Space is not a thing in itself, but a set of relationships between objects. Remove the objects, and space disappears. The same applied to time. For Leibniz, time was the order of successive events. Without change, there is no passage of time. In his correspondence with Clarke, Leibniz criticized Newton's absolute framework as metaphysically extravagant and theologically problematic. Why, he asked, would God create an empty container if nothing existed within it? This debate between Newtonian absolutism and Leibnizian relationalism would echo through the centuries, resurfacing in different forms as science progressed. But for the next 200 years, Newton's view held sway. His framework was extraordinarily successful in practice. It allowed engineers to build bridges and canals, astronomers to predict eclipses, and navigators to chart the seas. It gave rise to classical mechanics, the foundation of physics, until the early 20th century. Part of the reason for this dominance was that Newton's model worked. Observations of planetary motion, especially those of Mars by Tycho Brahe and Johannes Kepler, matched Newton's predictions with extraordinary precision. The discovery of the planet Neptune in the mid-19th century, based on gravitational perturbations in the orbit of Uranus, was a stunning confirmation of Newtonian mechanics. These achievements gave classical physics an air of completeness, as though the great questions of motion and structure had been definitively answered. But the concept of nothingness remained somewhat ambiguous within this framework. Newton's absolute space could exist without matter, but it was not nothing in the deepest sense. It had geometry. It had duration. It provided measurable intervals and distances. It allowed for the propagation of forces such as gravity. In that sense, it was a kind of structured emptiness, a container but one with properties. Even Newton's theory of gravity depended on action at a distance, where masses exerted forces on each other across empty space. This raised new questions. How could one object influence another without a medium between them? What was the mechanism of gravitational attraction? Newton himself was uneasy with the idea. In a letter to Richard Bentley, he wrote that gravity should be innate, inherent, and essential to matter is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Yet he had no alternative to propose. In time, physicists would search for such a mechanism, introducing ideas like the luminiferous ether, a hypothetical substance thought to permeate all space and carry waves of light, much like air carries sound. The ether was imagined as invisible, intangible, and undetectable by ordinary means. It was, in effect, a modern version of the ancient idea that the void could not be truly empty. But the ether, like so many placeholder concepts in science, would not survive experimental scrutiny. By the late 19th century, the famous Michelson-Morley experiment demonstrated that the speed of light remained constant regardless of the Earth's motion through space. This result posed a serious challenge to the ether hypothesis and set the stage for a radical new understanding of space and time. Before that transformation could occur, however, Newton's framework had to run its course. It remained the dominant paradigm through the Enlightenment and the Industrial Revolution. It shaped the way scientists, philosophers, and laypeople alike imagined the cosmos. Even today, Newtonian space and time persist as useful approximations in everyday life. For launching satellites, constructing buildings, or modeling mechanical systems, the classical view still applies with high accuracy. Yet as physicists probed deeper into the fabric of reality, they began to discover that the Newtonian assumptions, particularly the ideas of absolute space and absolute time, were not universally valid. The emergence of electromagnetism, thermodynamics, and especially quantum theory revealed layers of complexity that classical physics could not explain, and the nature of the vacuum, long treated as a simple absence, turned out to be far more dynamic and strange than anyone had imagined. The limitations of Newton's model became undeniable at the dawn of the 20th century, when a young patent clerk in Switzerland proposed a revolutionary idea: that space and time are not fixed, separate entities, but part of a unified, flexible geometry that bends and warps in response to mass and energy. The cracks in Newton's framework became increasingly visible by the late 19th century. As physicists explored the behavior of light, electricity, and magnetism, they began to encounter phenomena that Newtonian mechanics simply could not explain. One of the most puzzling discoveries was that the speed of light appeared to be constant, regardless of how fast the observer or the source of light was moving. This defied the logic of classical motion, and it pointed toward a deeper structure hiding beneath space and time. Into this growing uncertainty stepped Albert Einstein. In the year 1905, a year now celebrated as his annus mirabilis, or miraculous year, Einstein published 4 groundbreaking papers. Among them was his special theory of relativity, a radical rethinking of space, time, and motion. He was only 26 years old, working at the Swiss Patent Office in Bern, and yet the clarity of his insight would transform physics forever. Einstein's core idea in special relativity was deceptively simple. The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is constant for all observers, no matter how fast they are moving. But these 2 principles had profound consequences. They meant that time and space could no longer be considered absolute. Observers moving at different speeds would experience different durations of time and different lengths of space. Events that appeared simultaneous to one observer might not appear so to another. This shattered the Newtonian idea of a universal clock ticking away in the background of the cosmos. In Einstein's new vision, time was not separate from space. Instead, they were interwoven into a single 4-dimensional continuum, what we now call space-time. The mathematical development of this idea owed much to the work of Hermann Minkowski, a German mathematician who had been one of Einstein's professors. In a lecture delivered in the year 1908, Minkowski famously declared, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the 2 will preserve an independent reality." He recast Einstein's theory in geometric terms, showing how events could be represented as points in a 4-dimensional space-time manifold, where time acted as the 4th dimension. This was not just an elegant reformulation, it was a crucial step forward. It allowed physicists to begin visualizing how time and space could bend, stretch, and shift depending on motion and gravity. But the true leap came a decade later, when Einstein extended his ideas beyond special relativity into a fully general theory. In the year 1915, after years of intense struggle and correspondence with mathematicians like Marcel Grossmann, Einstein completed his general theory of relativity. This new theory redefined gravity itself, not as a force, as Newton had described, but as the curvature of space-time caused by mass and energy. Massive objects like stars and planets warped the geometry of the space around them, and this curvature guided the motion of other objects. In simple terms, matter tells space-time how to curve, and curved space-time tells matter how to move. One of the most striking features of general relativity was that it removed the need for a background container. Space was no longer a passive stage, it was an active, dynamic participant. And since time was part of this structure, it too could stretch or contract under different gravitational conditions. A clock near a massive body, for example, would tick more slowly than one farther away, a phenomenon later confirmed by atomic clocks flown on airplanes and satellites. Einstein's theory also predicted the existence of black holes, regions where space-time curvature becomes so extreme that nothing, not even light, can escape. And it laid the groundwork for understanding the universe as a whole, including its origin and large-scale structure. One of the first major tests of general relativity came in the year 1919 during a solar eclipse. British astronomer Arthur Eddington led an expedition to the island of Principe off the coast of West Africa, where he photographed starlight passing near the sun. According to Einstein's theory, the sun's gravity should bend the light, making stars appear slightly out of place. Eddington's measurements confirmed the prediction, making Einstein an international celebrity and establishing general relativity as the new foundation for gravitational physics. But as successful as the theory was, it also introduced new questions. If space-time could bend and evolve, what did this imply about the universe as a whole? Could space-time itself have a beginning or an end? And if so, what would it mean for something to come into being from the absence of space and time? These questions were not answered immediately. For a time, even Einstein resisted the idea of a dynamic universe. His original field equations allowed for expanding or contracting solutions, but he disliked the implications and added a term, the cosmological constant, to force a static universe. It was not until the work of Alexander Friedmann in the early 1920s and later Georges Lemaitre that the expanding universe became a serious scientific hypothesis. Their models, based on general relativity, showed that space-time could evolve and that it might have originated from a highly dense state, a concept that would later become the Big Bang theory. With this new framework, the idea of nothing underwent another transformation. In Newton's universe, space and time were ever-present containers, even if matter was removed. In Einstein's universe, space and time were physical, mutable, and contingent upon energy and geometry. They could stretch, shrink, and, at least theoretically, emerge or vanish. This opened a door to a more nuanced understanding of the early universe. If space and time themselves could have a beginning, then the notion of a void before the universe became even more complicated. What would it mean to speak of before time if time itself was part of what emerged? What would it mean to imagine a location, a region of space, prior to space existing? These were no longer merely philosophical riddles. They were now mathematical questions. Questions to which physicists could begin applying the tools of geometry, field theory, and differential equations. General relativity gave science the language to describe the birth of space and time not as metaphysical abstractions, but as events in a physical process. Even so, general relativity was not the final word. While it describes gravity with exquisite precision, it does not incorporate quantum mechanics, the theory that governs particles, forces, and energy at the smallest scales. As physicists continued to explore the earliest moments of the universe, they would find that both frameworks, relativity and quantum theory, were essential, and yet fundamentally incompatible in their current forms. This tension would drive the next phase of inquiry, a search for a deeper understanding of the vacuum, for quantum fluctuations that might give rise to matter and structure, and for models of the cosmos that could reconcile the infinite density predicted by relativity with the probabilistic nature of quantum fields. Einstein's theory had revealed that space and time were not immutable backdrops, but could stretch, curve, and evolve. Still, the full implications of a dynamic cosmos remained largely untested in the early decades of the 20th century. While the equations of general relativity allowed for expansion or contraction, most physicists, including Einstein himself, assumed the universe was static and eternal. That view would soon be challenged by a set of careful astronomical observations that rewrote the story of the cosmos. The person most famously associated with this transformation is Edwin Hubble. Born in the late 19th century in Marshfield, Missouri, Hubble originally studied law at Oxford before turning to astronomy, a decision that would change the field forever. By the early 1920s, he was working at the Mount Wilson Observatory in California, home to the most powerful telescope in the world at that time, the 100-inch Hooker telescope. Hubble's work initially focused on a class of mysterious, faint objects known as nebulae. For centuries, astronomers had debated whether these nebulae were part of our own Milky Way galaxy or distant star systems in their own right. The question was more than academic. It bore directly on the scale of the universe. If the nebulae were within the Milky Way, then the cosmos might be relatively small and self-contained. If they were beyond, it would mean that the universe was far larger than previously imagined. To resolve this, Hubble used a special kind of star known as a Cepheid variable. These stars have a predictable relationship between their brightness and their pulsation rate, discovered by Henrietta Swan Leavitt at the Harvard College Observatory in the early 20th century. By measuring how fast a Cepheid pulses, astronomers can determine its absolute brightness. Comparing that with how bright it appears from Earth gives a direct estimate of its distance. Using this method, Hubble studied the Andromeda Nebula and found it was far too distant to be part of the Milky Way. It was, in fact, an entirely separate galaxy. In one stroke, the universe expanded, not in the sense of physical growth, but in human understanding. The Milky Way was no longer the entirety of the cosmos. It was just one galaxy among many. But Hubble's most important contribution was yet to come. Working with his colleague Milton Humason, Hubble began measuring the redshift of galaxies. Redshift refers to the way light stretches toward longer wavelengths as objects move away from the observer, a kind of cosmic Doppler effect. What Hubble and Humason found was astonishing. Almost every galaxy they studied appeared to be moving away from us, and the farther away it was, the faster it was receding. In 1929, Hubble published a paper demonstrating a linear relationship between a galaxy's distance and its redshift. This became known as Hubble's law. It implied that the universe was not static, but expanding. Space itself was stretching, carrying galaxies with it like raisins in a rising loaf of bread. The implications were immense. If the universe was expanding today, then it must have been smaller in the past. Extrapolated backward, it would have once been condensed into an extremely hot, dense state. This observation lent powerful support to theoretical models that had already suggested an expanding cosmos. Russian physicist Alexander Friedmann in the early 1920s had developed solutions to Einstein's field equations showing that the universe could expand or contract. Independently, Belgian physicist and priest Georges Lemaitre proposed in 1927 that the universe began as a primeval atom that exploded outward, an idea that anticipated what would later be called the Big Bang. Einstein initially resisted these implications. When shown Lemaitre's work, he reportedly dismissed it, saying, "Your calculations are correct, but your physics is abominable." Einstein had even introduced a term into his equations, the cosmological constant, to force a static solution, believing that the universe could not be dynamic. But after Hubble's findings, he retracted that position and is said to have called the cosmological constant the greatest blunder of his life, though historians debate whether he ever used those exact words. The idea of an expanding universe transformed cosmology from a philosophical exercise into a rigorous scientific field. For the first time, astronomers could speak meaningfully about the history of the cosmos. If the universe had once been smaller and denser, it might have had a beginning. And if it had a beginning, then what lay before it? This question did not yet have an answer. The term Big Bang was actually coined later, in the mid-20th century, by British astronomer Fred Hoyle, ironically as a term of ridicule for a theory he opposed. Hoyle favoured a steady-state model in which the universe expands but matter is continuously created to maintain a constant density. This model preserved an eternal universe with no beginning and no need to confront the troubling question of origins. But the evidence continued to mount against the steady-state view. In the year 1965, Arno Penzias and Robert Wilson at Bell Telephone Laboratories were experimenting with a radio antenna when they encountered a persistent background noise. They could not eliminate it, no matter how they adjusted the equipment. Unbeknownst to them, physicists Robert Dicke and Jim Peebles at Princeton University were developing a theory predicting exactly such a signal, a faint glow left over from the early universe, cooled by billions of years of cosmic expansion. The noise Penzias and Wilson had discovered turned out to be the cosmic microwave background radiation, a relic of the hot, dense, early universe. This accidental discovery provided strong empirical support for the Big Bang model. The universe had not always existed in its current form. It had evolved, and it had a past. With this new understanding, the concept of nothing took on even deeper significance. If the universe had a beginning, then what were the conditions at the moment of its birth? Was it born from a singularity, a point of infinite density and zero volume? Did time itself begin at that moment, or was there something before? These were no longer purely speculative questions. They were grounded in observation, shaped by precise measurements and theoretical models. Edwin Hubble's work thus marks a pivotal turning point. He did not invent the idea of the expanding universe, nor did he develop the theoretical framework behind it. But his observations provided the crucial evidence needed to bring the idea into the scientific mainstream. Without the redshift-distance relationship he uncovered, the Big Bang might have remained a fringe hypothesis. His findings also forced physicists to confront the temporal dimension of the cosmos. The universe was not merely expanding in space, it was evolving in time. And if it had a beginning, then the concept of nothing before that beginning demanded new and careful thought. As the scientific community began to explore the implications of this beginning, attention turned toward the very nature of that initial state. Could general relativity describe it all the way down to the first instant, or did something break down? Did the equations point to a singularity, a mathematical indication that physics itself might no longer apply? To pursue those questions, researchers would soon look beyond geometry and gravitation to the realm of quantum theory, where uncertainty and probability replace certainty and continuity. But first, the mathematical consequences of Einstein's theory would reveal something even more dramatic, that under certain conditions, space and time themselves must have a beginning, a conclusion drawn not from speculation, but from rigorous proof. As the idea of an expanding universe gained momentum, the implications of a cosmic origin point began to attract more serious scientific attention. With observational evidence building steadily, especially after the discovery of the cosmic microwave background radiation, the Big Bang theory gradually evolved from a speculative model into the prevailing explanation for the origin and evolution of the universe. But behind this transformation was a rich interplay of theory, data, and debate that shaped modern cosmology. The term Big Bang itself, now used universally to describe the birth of the universe, did not begin as a technical phrase. It was coined by British astrophysicist Fred Hoyle during a BBC radio broadcast in the year 1949. Hoyle was an advocate of the competing steady-state theory, and he used the phrase somewhat dismissively to contrast his own model with the idea that the universe had exploded into existence from a single, dense point. Ironically, the label stuck, eventually becoming the name of the very theory Hoyle opposed. The steady-state theory that Hoyle supported rested on the notion that the universe, though expanding, maintained a constant density over time. This required that new matter be continuously created to fill the gaps as galaxies moved apart. The appeal of this model lay in its philosophical simplicity. It implied an eternal, unchanging universe with no beginning and no end, sparing scientists from confronting the thorny question of origins. But as more data emerged, the steady-state model began to falter. In particular, the discovery of the cosmic microwave background radiation in the mid-1960s provided compelling evidence for a hot, dense early universe, precisely the kind of relic that the Big Bang theory predicted. This radiation, a faint afterglow of the primordial fireball, had been cooling and stretching with the expansion of space for billions of years. Its detection, first by Arno Penzias and Robert Wilson, and later mapped in detail by the COBE satellite and subsequent missions, was one of the most significant confirmations in the history of cosmology. With the observational foundations strengthening, scientists turned to refining the theoretical framework of the Big Bang. Among the most important figures in this effort was George Gamow, a Russian-American physicist who, in the 1940s, began developing a model of the early universe in which it was hot enough for nuclear reactions to occur. Working with Ralph Alpher and Robert Herman, Gamow predicted that the early universe would produce light elements like hydrogen, helium, and traces of lithium in specific ratios. This process, known as Big Bang nucleosynthesis, became a powerful test of the theory's validity. Their predictions match closely with observed abundances of these elements, further cementing the theory's credibility. While this alone did not prove the Big Bang, it helped establish that the early universe had passed through a hot, dense phase, something the steady-state model could not easily accommodate. As theoretical and observational tools advanced throughout the 20th century, the Big Bang model grew increasingly sophisticated. It was no longer seen as a simple explosion of matter into empty space. Instead, it was understood as the rapid expansion of space itself from an extremely compact state. The early universe was not a point in space, but a state of energy and density that existed everywhere at once. The expansion was not into a pre-existing void. It was the stretching of space-time itself. This idea corrected a common misconception. The Big Bang did not occur at a single spot in a pre-existing vacuum. Rather, it happened everywhere in the universe simultaneously. From any given location, one would see other galaxies receding in all directions, as if from a central explosion. But this is a property of the metric expansion of space, not a blast into a surrounding emptiness. There was no outside into which the universe expanded. There was simply space coming into being and growing. One major challenge, however, remained. While the Big Bang theory explained many features of the cosmos, it did not account for why the universe looked so uniform and flat on large scales. Nor did it explain the near-perfect isotropy of the cosmic microwave background. These puzzles, known as the flatness problem, the horizon problem, and the monopole problem, suggested that something important was missing from the early narrative. That missing piece arrived in the form of inflation theory, proposed by physicist Alan Guth in the early 1980s. We will explore that theory in greater depth later, but briefly, inflation posits that in the first tiny fraction of a second after the Big Bang, the universe underwent a brief but stupendous burst of exponential expansion. This would have smoothed out any irregularities, stretched space flat, and driven the universe to the state we observe today. Inflation not only resolved several of the Big Bang model's puzzles, but also introduced the possibility that the entire observable universe might have arisen from an incredibly small, quantum-sized region. Yet even with the addition of inflation, the Big Bang theory did not provide a complete account of the universe's origin. It described how the universe evolved from an early hot, dense state, but it did not explain how or why that state came into being. General relativity, though powerful, breaks down under the extreme conditions of the initial singularity, where density and temperature become infinite. At that boundary, the equations cease to be meaningful. This is where the question of nothing begins to press in again. If the Big Bang marked the beginning of space-time, then what could have preceded it, if anything? Could there be a cause before time itself existed? Or is the question ill-formed? These are not just philosophical inquiries. They are scientific ones, and they require new theoretical tools to address. One early attempt to approach this boundary involved considering what kind of initial conditions might govern the birth of the universe. Stephen Hawking, along with James Hartle, would later propose a bold model suggesting that time itself may have had no boundary, that the universe might have no beginning in a traditional sense. But even before such ideas emerged, cosmologists were already grappling with a deeper mathematical question. Could general relativity itself predict the conditions under which the universe must have begun? This question led directly to the work of Stephen Hawking and Roger Penrose, who developed the singularity theorems in the late 1960s and early 1970s. These theorems showed that, under certain very general conditions, a universe obeying general relativity and containing mass energy must have originated from a singularity. In other words, time and space themselves must have had a beginning, a moment when classical physics could no longer describe reality, but the implications of the singularity were ambiguous. Was it a real physical entity, or a sign that our understanding of nature had reached its limits? Either way, it pointed to the need for a new framework, one that could unify quantum theory with general relativity, because at the birth of the universe, both gravity and quantum effects must have been operating at extreme levels. As physicists moved into this new frontier, they began to explore quantum cosmology, quantum gravity, and the nature of spacetime at the smallest scales. These developments, while still in their early stages, began to redefine what nothing might mean. Not an empty void, but perhaps a quantum vacuum, a fluctuation, or even a probabilistic state outside of classical time. As the Big Bang theory became firmly rooted in both observational evidence and theoretical physics, it left behind a trail of unresolved questions, none more pressing than the singularity itself. What did it truly represent? Was it a real physical state, or merely a breakdown in our current understanding of physics? To probe this boundary, scientists needed to explore not just how the universe expanded from its early state, but whether there was a mathematically unavoidable point at which space and time themselves came into existence. This challenge was taken up most directly by two extraordinary thinkers, Stephen Hawking and Roger Penrose. Their work would lead to the development of the singularity theorems, mathematical proofs demonstrating that, under very general and physically realistic conditions, a singularity is not just a theoretical curiosity, but a necessary consequence of general relativity. The partnership between Penrose and Hawking was forged in the late 1960s, a time when the nature of black holes and the beginning of the universe were just beginning to be understood in mathematical detail. Roger Penrose, a mathematical physicist based in Britain, had already been exploring the structure of spacetime in extreme conditions. In the year 1965, he published a landmark paper proving that once a certain critical density is exceeded within a collapsing star, no known physical force can prevent its collapse into a singularity, a region of infinite curvature where general relativity ceases to function. This result came as a surprise. Up until that point, many physicists had assumed that singularities, if they appeared in theory, were simply artifacts of idealized models or special conditions, not physical realities. Penrose's work showed otherwise. His theorem was built not on symmetry or perfect conditions, but on general assumptions about gravity and energy. The implications were sobering. If massive stars could collapse into singularities, then perhaps the entire universe had once emerged from one. Enter Stephen Hawking. At the time, Hawking was a young physicist just beginning to make his mark. Inspired by Penrose's approach, he applied similar techniques to the expanding universe rather than a collapsing star. Working closely with Penrose, he formulated a new version of the singularity theorem, one that applied to cosmology. Their combined results suggested that, if the universe is expanding now and contains matter and energy, both of which are empirically true, then it must have originated from a singularity in the finite past. What exactly does this mean? In the language of general relativity, a singularity is a region where curvature becomes infinite, and geodesics, the paths that particles or light would follow, can no longer be extended. In more intuitive terms, it is a boundary to space and time, a point beyond which the fabric of reality cannot be described by the known laws of physics. The significance of the Hawking-Penrose singularity theorems is that they did not rely on specific details of the universe's contents or geometry. They were robust and general, showing that a singular origin is not a quirk of one model, but an almost inevitable consequence of general relativity itself. These results were widely celebrated, but also deeply unsettling. The idea of a singularity at the beginning of time posed profound conceptual problems. It implied that time itself may have had a starting point, that there may literally be no before the Big Bang in any physical sense. For many scientists, this raised a disturbing possibility. The laws of physics, as currently formulated, could not describe the origin of the universe. The singularity marked the limit of general relativity's domain. Beyond that point, space and time had no meaning, or at least none that classical physics could describe. But for Hawking and others, this was not the end of the story. Instead, it marked the beginning of a new line of inquiry. What happens when quantum effects are introduced into the picture? Stephen Hawking's brilliance lay in his ability to straddle the worlds of relativity and quantum theory, two frameworks that are notoriously difficult to reconcile. While general relativity governs the large-scale structure of space and time, quantum mechanics deals with the behavior of particles at the smallest scales. At a singularity, these two domains collide. One of Hawking's most famous contributions came in the form of Hawking radiation, a theoretical prediction that black holes are not entirely black but emit tiny amounts of thermal radiation due to quantum effects near their event horizons. This idea, proposed in the early 1970s, was the first serious attempt to blend general relativity with quantum field theory. It also introduced the idea that black holes could eventually evaporate, suggesting that singularities might not be the eternal, one-way dead ends they were once thought to be. Although Hawking radiation applied to black holes, it had important implications for cosmology. If quantum effects could alter the classical picture of singularities in black holes, perhaps they could do the same for the Big Bang. Perhaps the singularity at the beginning of the universe was not truly a point of infinite density, but rather a boundary where classical physics gave way to a new quantum description of the cosmos. This line of thinking eventually led Hawking to collaborate with James Hartle on what would become known as the no-boundary proposal. We will examine that model more deeply later, but its basic idea was that time, near the beginning of the universe, behaved more like a spatial dimension, eliminating the notion of a sharp beginning or edge. In this view, the universe was finite but without boundary, like the surface of a sphere, which is complete and smooth but has no edge or center. Even with such elegant ideas emerging, the singularity theorems retained their foundational role. They established that any attempt to explain the origin of the universe must confront the breakdown of classical physics. The existence of the singularity was not simply an open question, it was a mathematical certainty given the assumptions of general relativity and our observed universe. These theorems also shifted the focus of cosmology. Rather than merely describing how the universe evolves, scientists were now compelled to ask how the laws of physics themselves emerge. Could space-time and its geometry be the result of deeper quantum principles? Could the universe tunnel into existence from a prior quantum state? Moreover, the singularity theorems raised the stakes for developing a theory of quantum gravity, a unified framework that could describe the behavior of gravity at quantum scales. Without such a theory, our understanding of the beginning remains incomplete. Today, physicists continue to explore candidates for such a theory, including loop quantum gravity, string theory, and other speculative models. But the questions first sharpened by Hawking and Penrose remain. Is the singularity real, or just a signpost pointing beyond current physics? Can the concept of nothing be made meaningful within a quantum framework? And if space and time had a beginning, what, if anything, could lie beyond that boundary? The answers to these questions require not only mathematics, but also new physical insight, because the singularity does not merely mark the edge of a theory, it marks the limit of what space and time themselves can mean. With the singularity theorems of Hawking and Penrose exposing the limits of classical physics, the attention of cosmologists naturally shifted toward quantum mechanics. If general relativity could describe the evolution of spacetime, but not its origin, then perhaps quantum theory, which governs the behavior of matter and energy at the smallest scales, might offer insights into what lies at, or even beyond, the singularity. But to enter the quantum world is to abandon many of our everyday intuitions, including what we think we know about nothing. In classical physics, a vacuum is often defined as empty space, a region devoid of matter and energy. But quantum theory paints a far stranger picture. According to quantum field theory, even the most empty regions of space are alive with activity. Particles flicker into and out of existence. Fields ripple with fluctuations. Energy is never truly zero, even in a vacuum. In this new framework, nothing is no longer nothing. The foundation of this revolution began in the early 20th century as physicists grappled with phenomena that defied classical explanation. Max Planck introduced the idea of quantized energy levels in the year 1900, marking the birth of quantum theory. Soon after, Albert Einstein explained the photoelectric effect by suggesting that light itself comes in discrete packets called photons. Niels Bohr introduced a model of the atom in which electrons occupy quantized orbits, and Werner Heisenberg, Erwin Schrödinger, and Paul Dirac each contributed to the mathematical structure that would become quantum mechanics. Among the most unsettling discoveries of this new physics was the uncertainty principle formulated by Heisenberg. It stated that certain pairs of physical quantities, such as position and momentum, could not both be known with perfect precision. This was not due to any flaw in measurement, but rather a fundamental feature of nature. In the quantum realm, particles do not have exact positions or velocities until they are observed. Instead, they exist as probabilities, waves of potentiality that collapse into specific outcomes only when measured. This inherent fuzziness extended to the concept of energy. According to the energy-time uncertainty relation, even the energy of a system could fluctuate, provided the fluctuation occurred over a very short timescale. This implied that in a vacuum, defined as a region with no particles or radiation, there could still be temporary energy fluctuations. These fluctuations, in turn, could produce pairs of virtual particles that briefly exist and then annihilate each other, returning their borrowed energy to the vacuum. This phenomenon was not mere theory. It produced measurable consequences. In the 1940s, physicist Hendrik Casimir predicted that two uncharged parallel metal plates placed very close together in a vacuum would experience an attractive force. This Casimir effect arises because the quantum vacuum between the plates is constrained, altering the allowed modes of fluctuation compared to the surrounding space. In the decades that followed, the effect was confirmed experimentally with remarkable precision. The vacuum, it seemed, was anything but empty. It was a sea of invisible energy and fluctuating fields, governed by the probabilistic rules of quantum mechanics. Paul Dirac's theory of the electron, formulated in the late 1920s, further reinforced this idea. His equations predicted the existence of antimatter, a mirror version of matter with opposite charge, which was later confirmed by the discovery of the positron. To account for these predictions, Dirac introduced the concept of the Dirac sea, a theoretical model in which all negative energy states are filled in the vacuum and excitations within this sea appear as particles. Quantum electrodynamics, the quantum theory of electromagnetic interactions, soon emerged to provide a more refined and accurate description. Developed by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, this theory showed that even the behavior of particles in empty space was shaped by the endless dance of virtual particles and fields. It became one of the most successful theories in physics, capable of predicting the magnetic moment of the electron to an astonishing number of decimal places. By the late 20th century, the concept of a quantum vacuum had become central to particle physics. The so-called standard model of particle physics, our most complete description of fundamental particles and their interactions, relies heavily on the idea of vacuum fields. The Higgs field, for instance, is a quantum field that permeates all of space. Particles acquire mass through their interaction with this field. Even in the vacuum state, the Higgs field has a non-zero value, meaning that the vacuum is not empty, it has structure. The discovery of the Higgs boson in the year 2012 at CERN's Large Hadron Collider was a striking confirmation of this idea. The Higgs boson is an excitation of the Higgs field, much like a ripple on a pond. Its detection proved that the vacuum is filled with active, physical fields, whose presence shapes the behavior of matter and energy throughout the universe. This has profound implications for cosmology. If the vacuum is not truly empty, but filled with energy and fields, then it is not hard to imagine how a universe might emerge from such a state. The concept of vacuum fluctuations, temporary and spontaneous variations in energy, leads to the possibility that under the right conditions, such a fluctuation could become permanent, inflating into a full-fledged universe. Physicist Edward Tryon was among the first to suggest this explicitly in the early 1970s. He proposed that the universe might be a quantum fluctuation of the vacuum, a momentary blip that, under certain conditions, became stable and began expanding. This idea was speculative, but it introduced the bold possibility that our entire cosmos might have emerged from what appears, at first glance, to be nothing. In quantum mechanics, the line between something and nothing becomes blurry. A quantum vacuum contains no particles in the classical sense, but it is not devoid of activity or structure. It is defined by a ground state, the lowest possible energy configuration of a field. But even that state is dynamic and filled with potential. This leads to a counterintuitive but rigorous idea. Nothingness, as traditionally conceived, may not exist in the physical universe. This perspective opens the door to a new understanding of cosmic origins. Instead of requiring a divine spark or an external cause, the universe might arise spontaneously from a quantum vacuum governed by known physical laws. But such a scenario also raises questions. What determines the structure of the vacuum? What laws govern its behavior? And can such a vacuum exist without a background space-time? These questions lie at the edge of quantum field theory and the emerging field of quantum cosmology. While many of the details remain speculative, one thing is clear: the vacuum is not the passive emptiness imagined by classical physics. It is a dynamic, energetic, and law-governed foundation that may hold the key to understanding how the universe emerged without violating physical principles. By redefining emptiness, quantum mechanics redefined the boundaries of origin. It showed that even nothing is full of potential, and that the seeds of creation might lie in the most subtle fluctuations of space and energy. But if the universe truly emerged from such a quantum vacuum, how did it become the vast, smooth, and structured cosmos we see today? What mechanism allowed a tiny fluctuation to inflate into everything we know? If quantum mechanics revealed that even the vacuum was not truly empty, then the next question became clear. How could such a restless, fluctuating vacuum give rise to the structured, smooth, and vast universe we inhabit? While the Big Bang theory, supported by cosmic microwave background radiation and the observed expansion of the universe, provided a framework for cosmic evolution, it left several deep puzzles unresolved. Chief among them were the horizon problem, the flatness problem, and the problem of initial irregularities. The solution to these mysteries arrived not through a complete overhaul of physics, but through a subtle and powerful addition, a brief moment of exponential expansion known as inflation. The idea of cosmic inflation was introduced in the early 1980s by physicist Alan Guth. Working at the Massachusetts Institute of Technology, Guth was investigating a theoretical phase transition in the early universe rooted in particle physics. As he explored how symmetry breaking might occur in grand unified theories, frameworks that attempt to unify the strong, weak, and electromagnetic forces, he stumbled upon a startling implication. Under certain conditions, the early universe could have undergone an extremely rapid, exponential expansion that smoothed out any initial irregularities. This insight became the foundation of the inflationary model, a bold proposal that suggested the universe expanded not steadily but violently and briefly, growing by a factor far greater than previously imagined in an unimaginably small fraction of a second. To appreciate the significance of this idea, one must first understand the problems it was designed to solve. The horizon problem refers to the striking uniformity of the cosmic microwave background radiation, the afterglow of the early universe. Observations show that regions of the sky separated by vast distances have nearly identical temperatures. Yet, under the standard Big Bang model, those regions should not have had time to exchange information or energy, since light would not have had time to travel between them. In other words, there has not been enough time since the beginning of the universe for those regions to come into thermal equilibrium. So why are they so similar? The flatness problem is related but distinct. Measurements of the large-scale geometry of the universe show that it is extremely close to flat, meaning that parallel lines remain parallel over cosmic distances. But this flatness is unstable. If the early universe had been even slightly curved, either positively or negatively, the curvature would have grown over time, leading to a universe that would look drastically different today. The fact that the universe is still nearly flat suggests that its initial conditions had to be extraordinarily fine-tuned. The monopole problem arose from theoretical predictions in grand unified theories. These models suggested that the early universe should have produced a large number of magnetic monopoles, hypothetical particles that carry a single magnetic charge, either north or south. Yet no monopoles have ever been observed, raising the question of where they went. Guth's theory of inflation resolved all three problems in one elegant stroke. If the universe expanded exponentially during the first tiny fraction of a second after its birth, then regions that are now far apart could once have been in close contact, allowing them to reach the same temperature. As space expanded, it stretched those regions apart faster than light could travel between them, freezing in their uniformity. This solves the horizon problem. At the same time, inflation would have stretched the curvature of the universe toward flatness, just as blowing up a balloon flattens any small wrinkles on its surface. This naturally explains why the universe appears so flat today, without requiring exquisitely tuned initial conditions. And by diluting any exotic particles such as monopoles across an enormous volume of space, inflation explains why we do not observe them now. Guth published his paper on inflation in the year 1981, titled Inflationary Universe, a Possible Solution to the Horizon and Flatness Problems. It marked a turning point in cosmology, but the original version of the theory, later dubbed Old Inflation, had a flaw. It predicted that inflation would end through a process called bubble nucleation, where pockets of lower energy vacuum would form and expand. However, the bubbles would not merge smoothly, leading to an inhomogeneous universe, contradicting observations. This problem led to refinements of the theory. In the mid-1980s, physicist Andre Linde introduced what became known as new inflation, and later chaotic inflation. These versions avoided the bubble collision issue by using different models of the inflationary field, now called the inflaton. Instead of tunneling from one state to another, the inflaton field gradually rolled down a potential energy landscape, allowing inflation to end smoothly and transition into the standard Big Bang expansion. These modifications not only fixed technical issues but also opened the door to even more speculative ideas. In some versions of inflation, the process never fully ends but continues in different regions of space, spawning new bubble universes in a growing multiverse. While this idea lies beyond direct observation, it flows naturally from the mathematics of eternal inflation and has become a serious topic of investigation. The power of the inflationary model lies not only in its ability to solve long-standing puzzles, but in its predictive capacity. Inflation predicts a nearly scale-invariant spectrum of density fluctuations, tiny differences in the distribution of matter that would later grow into galaxies, clusters, and large-scale cosmic structures. These fluctuations arise from quantum perturbations in the inflaton field, stretched to cosmic scales during inflation and imprinted on the fabric of spacetime. When the cosmic microwave background was measured in detail by the Kobe satellite in the early 1990s, and later by the WMAP and Planck missions, the data matched inflationary predictions with stunning precision. The tiny temperature variations observed across the sky reflected the same statistical patterns that inflation had forecasted. These ripples, on the order of 1 part in 100,000, became the seeds of all structure in the universe. It is a remarkable idea that the galaxies, stars, planets, and ultimately life itself owe their existence to minute quantum fluctuations in a field that operated during the first sliver of a second after the universe began. Inflation bridges the smallest and largest scales, uniting quantum uncertainty with cosmic architecture. Yet despite its success, inflation is not without critics. Some physicists argue that the theory is too flexible, capable of accommodating a wide range of observations without being easily falsifiable. Others question whether the inflaton field is real or merely a placeholder for deeper physics we do not yet understand. Still, inflation remains the leading explanation for the early dynamics of the universe. It reframes the question of nothing yet again, not as a void, nor even as a quantum vacuum, but as a state dominated by a high-energy field poised to unleash an exponential expansion. If the right conditions arise, conditions permitted by quantum theory, then inflation can begin. And from that moment, space and time grow, structure forms, and a universe emerges. Alan Guth once described his experience of discovering inflation as the most exciting moment of his life. In a notebook entry dated December the 27th, he simply wrote, "Spectacular realization." That realization has since reshaped how we think about the cosmos and about origins. But while inflation tells us how the universe grew from something very small into something vast, it still does not explain where the inflating state itself came from. Could that high-energy state arise spontaneously? Was it the result of a quantum fluctuation in a pre-existing field? Or does it hint at something deeper still? If inflation theory showed how the universe could grow from a microscopic seed to cosmic proportions, it still left one vital question open. Where did that seed come from in the first place? What caused inflation to begin? In the traditional Big Bang model, the initial state of the universe was simply assumed: hot, dense, and rapidly expanding. Inflation refined that description, but similarly left its own starting conditions unexplained. To address that gap, scientists began looking more deeply into the strange and unpredictable world of quantum mechanics, seeking answers that might explain how the universe could emerge not just from a field, but from nothing at all. This line of inquiry marked a subtle but profound shift. The question was no longer simply how the universe expanded, but why it started at all. And at the heart of this shift was the realization that quantum theory, with its probabilistic rules and energy fluctuations, might allow the universe to originate spontaneously, not from a prior universe, not from a timeless void, but from a vacuum state governed by the laws of quantum physics. One of the earliest and boldest voices in this domain was Edward Tryon, a physicist who, in the early 1970s, proposed that the universe might be a quantum fluctuation. In a short but provocative paper published in the journal Nature, Tryon suggested that the universe could have emerged from a vacuum in the same way that virtual particles appear in quantum field theory, spontaneously, briefly, and unpredictably. The twist in his proposal was that, under the right conditions, such a fluctuation could persist, grow, and evolve into an entire cosmos. Tryon's idea was met with both interest and skepticism. Could the universe really be a free lunch, as some later dubbed it, requiring no initial energy input? In his formulation, the total energy of the universe could be zero, balanced between the positive energy of matter and the negative energy of gravity. If so, then no conservation laws would be violated by the universe simply popping into existence. This notion was not mere speculation. It was grounded in the principle that in quantum mechanics, anything not forbidden by the laws of physics is permitted to occur, however unlikely. In a universe where time itself is emergent, the concept of causality before time loses meaning. The universe, in this view, might simply be not caused, but allowed. Building on these ideas, a more detailed quantum cosmological framework began to take shape. In the 1980s, physicists like Alexander Vilenkin, Andrei Linde, and James Hartler contributed key insights that brought clarity and structure to this bold vision. Vilenkin, in particular, developed a model in which the universe could originate through a quantum tunneling event. Quantum tunneling is a well-established phenomenon in quantum physics. It allows particles to pass through energy barriers that, under classical laws, would be impenetrable. Electrons in semiconductors, for instance, tunnel between energy states in transistors, a process that underpins modern electronics. In radioactive decay, particles tunnel out of atomic nuclei. This is not just a theoretical curiosity, it is a measurable and reliable effect. Vilenkin proposed that the universe itself could tunnel from a state of nothing, defined not as empty space, but as the absence of space and time, into a small, closed geometry that then inflates into a full universe. In this model, the probability of such a tunneling event is not zero, and once it occurs, inflation takes over and drives the expansion of space. The universe thus has no classical precursor. It arises through a quantum transition from a state of pure potentiality. Importantly, the nothing in these models is not the kind of nothing imagined in everyday language. It is not a vacuum in space, nor is it a cold void waiting in darkness. Rather, it is a state with no classical space-time geometry at all, a realm outside of time, governed by the probabilistic rules of quantum mechanics. In this context, nothing is a label for the absence of classical conditions, not the absence of all structure. Vilenkin's model made an important prediction. The universe that tunnels into existence should be closed and compact, much like the surface of a sphere. It begins at zero size and rapidly grows. This geometry is consistent with certain inflationary models and helps explain the overall homogeneity and isotropy of the observable universe. Around the same time, James Hartley and Stephen Hawking proposed a related but distinct approach, now known as the no-boundary proposal. We will explore that model more deeply in the next section, but its general thrust was to treat the universe's beginning not as a singular point, but as a smooth, boundaryless geometry. In both approaches, the laws of quantum mechanics govern the transition from non-existence to existence, not through deterministic causes, but through probabilities. One of the most remarkable aspects of these quantum cosmology models is that they shift the focus from initial conditions to initial probabilities. Instead of assuming that the universe started in a particular way, they ask, given all possible ways the universe might begin, which are more probable? This perspective opens the door to a broader landscape of possible universes, each with its own laws, geometries, and evolutions. Vilenkin and others have argued that among the set of allowed universes, those with inflation are exponentially more likely. Inflation not only solves cosmological problems, but becomes a statistical attractor, a natural outcome in the quantum probability space. The emergence of inflation, and therefore of a universe like ours, is not a fluke, but the most probable result of the quantum conditions preceding classical spacetime. Still, not all physicists are convinced. Some argue that the idea of time emerging from a timeless state is too speculative, or that the notion of tunneling from nothing lacks clear empirical grounding. Others question the assumption that energy balances to zero in a meaningful way, especially when general relativity complicates the definition of energy in a dynamic spacetime. Yet even among skeptics, there is agreement that quantum theory must play a central role in any explanation of the universe's origin. At the energies and scales involved, well beyond what current particle accelerators can probe, quantum gravity effects become dominant. Without a full theory of quantum gravity, whether it be through string theory, loop quantum gravity, or another approach, the exact mechanism of origin remains open. Despite these uncertainties, the models offered by Vilenkin, Tryon, and others provide a compelling narrative. They offer a framework in which the universe begins not through a miracle, nor through an arbitrary assumption, but as a natural outcome of the laws of physics. If correct, they suggest that nothing is not the absence of laws or possibility, but the most basic, minimal expression of what can happen. This leads to a startling conclusion. The universe may be inevitable, not predetermined in every detail, but inevitable in the sense that, given the structure of quantum theory and the nature of the vacuum, the emergence of something, of space, time, and matter, was bound to happen. And if that is true, then the question of what happened before the Big Bang may not even make sense. There was no before because time itself did not exist. Instead, we must think in terms of transitions, not sequences. The transition from non-existence to existence is not a moment in time, but the origin of time itself. If the quantum models of Edward Tryon and Alexander Vilenkin suggested that the universe could emerge spontaneously from a quantum state without violating the laws of physics, Stephen Hawking took the concept a step further. Alongside physicist James Hartley, he introduced a bold and elegant idea designed not just to describe how the universe might originate, but to redefine the question itself. What does it mean for the universe to have a beginning if time itself is part of what begins? This became the heart of the no-boundary proposal, a concept that challenged not only the structure of physics, but the limits of human intuition. It was an attempt to apply the principles of quantum mechanics to the entire cosmos, without relying on classical assumptions about time, causality, or spatial edges. In doing so, it offered a fresh way to understand what the phrase "before the Big Bang" might mean, and why, perhaps, it is the wrong question to ask. The no-boundary proposal emerged in the early 1980s, when Hawking and Hartley were exploring the intersection of general relativity and quantum mechanics. They recognized that describing the universe at its earliest moments required a new kind of framework, one that treated the entire cosmos as a quantum system. But how do you define a quantum wave function for the universe as a whole? What is the quantum state of everything? To approach this, they borrowed an idea from quantum field theory known as the path integral. In ordinary quantum mechanics, the path integral is a way of calculating the probability that a system evolves from one state to another by summing over all possible paths between those states. For example, a particle traveling from point A to point B does not take a single definite path. Instead, all conceivable paths contribute to the final probability, each weighted by a mathematical factor related to the action along that path. Hawking and Hartle extended this logic to cosmology. They proposed that the wave function of the universe could be found by summing over all possible geometries that the universe might have. Essentially, all the ways space-time itself could be shaped and structured. But this introduced a problem. If space-time had a beginning, then what boundary conditions should be applied at that origin? What kind of geometry existed at time zero? Their answer was both revolutionary and subtle. There is no boundary. More precisely, in their model, the universe is finite but without edges, just like the surface of a sphere, which has no boundary, even though it is not infinite. You can walk in any direction on a sphere and never reach a wall or an edge. Eventually, you come back to where you started. The no-boundary proposal applied this geometric logic to time itself. To make this work, Hawking and Hartle made use of a mathematical trick known as imaginary time. In classical physics, time is treated as a real number, running from the past to the future in a straight line. But in certain mathematical contexts, it can be treated like a spatial dimension by multiplying it by the square root of -1, denoted as I. This transforms time into a complex number, essentially rotating it 90 degrees into the realm of space. In imaginary time, the beginning of the universe becomes a smooth, rounded geometry, more like the south pole of the Earth than a sharp point. There is no singularity, no edge, and no moment where time suddenly springs into existence. Instead, the universe simply is, emerging smoothly from a quantum state without requiring a prior cause or an external framework. Hawking often explained this with a simple analogy. He would ask, "What is north of the North Pole?" The answer, of course, is that the question makes no sense. The North Pole is not a location with something beyond it. It is the boundary of latitude, the limit of the coordinate system itself. Similarly, in the no-boundary proposal, asking what happened before the beginning of time is like asking what is north of the North Pole. Time does not extend beyond the beginning because the beginning is not a point, but a smooth, rounded surface from which time unfolds. This idea resolved some of the key conceptual problems posed by the classical Big Bang model. In standard general relativity, the singularity at the beginning of the universe is a point of infinite curvature and density where the laws of physics break down. In the no-boundary model, the singularity is replaced with a smooth geometry governed by quantum rules. There is no need for an initial moment, no need for external boundary conditions, and no need for before. Mathematically, the Hartle-Hawking wave function describes the probability amplitude for different configurations of the universe. It tells us which geometries are more likely and under what conditions inflation might begin. Remarkably, their model suggests that inflation is not only possible but probable. Just as in Vilenkin's tunneling model, the geometries that give rise to inflation dominate the quantum landscape. This makes the emergence of a universe like ours not a rare event, but a statistically favored one. The no-boundary proposal has both fascinated and perplexed physicists and philosophers alike. Some have praised its elegance, calling it a natural extension of quantum principles to cosmology. Others have critiqued it for its reliance on imaginary time, which lacks a clear physical interpretation. Still others have questioned whether the path integral over all possible geometries is mathematically well defined. Despite these challenges, the model has had a profound influence. It introduced the idea that the universe's beginning could be geometrically natural, not imposed from the outside. It also illustrated how quantum cosmology might explain the origin of time and space without invoking anything beyond the laws of physics themselves. In later years, Hawking would refine the model and apply it to more specific cosmological questions, including the nature of entropy, the arrow of time, and the emergence of classical behavior from quantum systems. He remained committed to the idea that the universe, as he once put it, would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be. While the no-boundary proposal remains a theoretical model, one that has yet to be confirmed or ruled out by observation, it opened new avenues of thinking. It showed that the concept of a beginning need not involve a boundary, a trigger, or a singularity. Instead, the beginning of the universe could be the smoothest possible beginning, consistent with both general relativity and quantum mechanics. In this framework, nothing takes on a new meaning. It is not an empty void, nor a quantum vacuum, nor a singularity. It is the absence of classical time and space, replaced by a rounded quantum geometry from which our familiar universe gradually unfolds. It is not a place, nor a moment, but a transition, from timelessness to time, from potentiality to actuality. To many, this remains one of the most profound contributions of modern theoretical physics. It challenges the boundaries of what science can say, while remaining firmly rooted in mathematics and known physical laws. And it invites a deeper question still. If our universe can emerge from a no-boundary state, what determines which universe appears? As the no-boundary proposal redefined the nature of beginnings, removing the need for a singular point and suggesting a smooth quantum origin to space-time, it left behind a tantalizing possibility. If one universe could emerge from such a process, what would stop many from doing the same? Indeed, if the laws of quantum physics permit the spontaneous emergence of a universe like ours, governed by specific values of physical constants, might they not also permit the birth of many others, with different properties, different geometries, and perhaps even different laws? This question lies at the heart of the multiverse hypothesis, a collection of ideas that together suggest our universe may be just one among many. While it might seem speculative or even fantastical at first glance, the multiverse is not an invention of science fiction. It emerges naturally from serious efforts to understand the implications of quantum cosmology, inflation theory, and string theory. Though still unconfirmed, it now occupies a legitimate and active place in modern theoretical physics. One of the first clues pointing toward a multiverse came from the theory of eternal inflation, an extension of the inflationary model introduced by Alan Guth and later refined by Andre Linde. In standard inflation, a region of space undergoes rapid expansion for a brief period before transitioning into the slower, more stable expansion described by the Big Bang model. But in eternal inflation, this process never completely stops. Instead, while inflation ends in one region, causing it to become a bubble universe like ours, it continues in others, endlessly spawning new regions through quantum fluctuations. Each of these expanding regions becomes its own universe, with potentially different values of fundamental constants and distinct cosmic histories. In this picture, our universe is a single bubble in a vast cosmic foam, a small part of an eternally growing structure known as the inflationary multiverse. The mechanism behind eternal inflation is rooted in the probabilistic nature of quantum fields. The inflaton field, which drives inflation, does not decay uniformly. In some regions, quantum fluctuations push the field back up its potential, prolonging inflation. In other regions, the field decays and inflation ends, giving rise to a universe like ours. But since the process is stochastic, governed by random quantum variations, it guarantees that somewhere inflation always continues. There is no global end. The process is, quite literally, eternal. This idea has profound consequences. First, it means that the initial conditions of our universe may not be unique. Instead, they are one outcome among many possible configurations realized in different regions of the larger inflating space. Second, it implies that the laws of physics, which we observe with great precision in our local universe, may not be universally fixed. The values of the cosmological constant, the strength of gravity, the masses of elementary particles, these could all vary across the multiverse. This leads to the concept of the landscape, a term popularized by string theorists to describe the vast array of possible vacuum states allowed by string theory. In string theory, the fundamental building blocks of reality are not point particles, but tiny vibrating strings. The way these strings vibrate and the shape of the extra dimensions they inhabit determine the physical properties of the resulting universe. There are, by most estimates, an extraordinarily large number of possible configurations, perhaps as many as 10 to the 500th power. Each configuration corresponds to a different vacuum state with its own laws of physics. If inflation can populate this landscape, if each bubble universe can settle into a different vacuum state, then the multiverse becomes not just a speculative idea, but a natural outcome of our best theoretical models. The multiverse, in this sense, is not an optional extra. It is the structure that arises when quantum mechanics, inflation, and string theory are taken seriously together. One of the most controversial implications of this view is the application of anthropic reasoning. Since different universes have different physical properties, only a tiny subset may support the development of complex structures like stars, galaxies, and life. If the multiverse exists, then it is no longer surprising that we find ourselves in a universe with precisely the right conditions for life. We could not have appeared in a universe where life is impossible. Our universe is not fine-tuned by design. It is simply one where the conditions happen to allow observers to exist and ask the question. This idea, sometimes called the anthropic principle, has sparked vigorous debate. Critics argue that it abandons the goal of fundamental explanation, replacing it with a kind of cosmic lottery. If anything can happen somewhere, they say, then the theory becomes unfalsifiable. Others counter that the multiverse does make predictions. For instance, the distribution of values for the cosmological constant across the multiverse leads to a testable prediction about its value in our universe. That prediction, made in the late 1990s by physicist Steven Weinberg, correctly anticipated the discovery that the cosmological constant is small but non-zero, a result later confirmed by observations of cosmic acceleration. Still, the multiverse remains a challenging idea. By its nature, it may place much of reality beyond our observational horizon. The other bubble universes, if they exist, are causally disconnected from us. We cannot see them. We cannot send messages to them, but that does not mean they are not real. After all, there are parts of our own universe, beyond the observable horizon, whose light has not yet had time to reach us. We accept their existence because the laws of physics suggest continuity beyond what we can see. Physicists are now exploring ways to test multiverse theories indirectly. Some models predict that if two bubble universes collide, the event might leave an imprint in the cosmic microwave background, perhaps as a circular anomaly or subtle asymmetry. So far, no such signatures have been conclusively detected, but researchers continue to analyze high-precision data from telescopes like the Planck satellite. Meanwhile, the mathematics of eternal inflation and string theory continue to evolve. In recent years, new frameworks such as the string landscape, the swampland conjecture, and holographic models have deepened our understanding of what kinds of universes are theoretically possible. These developments suggest that the multiverse may not be as unconstrained as once feared. The range of viable universes may be limited by deep mathematical consistency, offering the hope of eventual testability. Whether the multiverse is a physical reality, a mathematical artifact, or a stepping stone to an even deeper theory remains an open question. But its rise within modern physics reflects a larger truth, that the search for cosmic origins inevitably challenges our assumptions about uniqueness, simplicity, and scope. If the multiverse exists, then our universe is no longer the totality of everything, but a single thread in a vast cosmic tapestry. And nothing in this context is not a singular void, but a landscape of possibilities, each one a different way that existence might unfold. In this expanded view, the question of what came before the Big Bang becomes less urgent. Our Big Bang is the beginning of our bubble, not of all reality. It is a local origin, a chapter in a far larger story. The multiverse reframes the question entirely, not why is there something rather than nothing, but why are we in this particular something out of so many possibilities? While the multiverse hypothesis offers a vast landscape of universes, each emerging from quantum processes or inflationary dynamics, it still leaves open one central issue: the fate of the singularity. Even with elegant proposals like the no-boundary condition or quantum tunneling models, there remains a critical point where general relativity breaks down and space-time, as classically understood, ceases to function. Is this truly the beginning, or could there have been something before? Could the Big Bang, rather than being the first act, be just a turning point in a longer, cyclical story? One of the most compelling responses to this possibility comes from loop quantum cosmology, a field born from the more general framework of loop quantum gravity. This approach attempts to do what physicists have long sought, to merge general relativity with quantum mechanics into a single, unified description of reality. But rather than building on string theory's extra dimensions and extended objects, loop quantum gravity works from a different angle. It reimagines space-time itself as discrete, built not from a continuous fabric, but from tiny, indivisible loops of quantum geometry. The idea at the heart of loop quantum gravity is that space is quantized. That is, just as energy comes in discrete units, or quanta, so too does the geometry of space. In this view, areas and volumes cannot be arbitrarily small. They come in finite chunks, defined by a mathematical structure called a spin network. These networks represent how space is woven together at the smallest scales, on the order of the Planck length, which is about 1/10,000,000th of a trillionth of a centimeter. From this foundation, loop quantum cosmology applies these principles to the universe as a whole. Rather than modeling space-time as a smooth continuum that breaks down at a singularity, it models it as a dynamic network that evolves in discrete steps. This leads to a remarkable result. The classical singularity is replaced by a quantum bounce. In this scenario, the universe does not begin with a point of infinite density. Instead, as the universe contracts, perhaps from a previous phase, it reaches a minimum volume where quantum gravitational effects become dominant. At this point, gravity effectively becomes repulsive, preventing further collapse. The result is a bounce. The universe stops contracting and begins to expand. The Big Bang, then, is not the beginning of time, but a transitional moment connecting a prior contracting universe to the current expanding one. This concept was first explored in detail by Abhay Ashtekar, one of the founders of loop quantum gravity, along with Martin Bojewald and other collaborators. Their work demonstrated that the equations governing loop quantum cosmology can be solved numerically, showing how the evolution of the universe proceeds smoothly through the bounce, with no singularity. The implications are profound. If true, it would mean that the question, what came before the Big Bang, is not meaningless, but answerable. There was a before, another phase of the universe's existence, governed by the same physical laws, but unfolding in reverse. Perhaps that phase had its own stars, galaxies, and structure, or perhaps it was smooth and featureless. Either way, it opens the door to a cyclical cosmology, in which the universe undergoes an eternal sequence of expansions and contractions, each connected by a bounce. This idea is not entirely new. Cyclical models have appeared throughout history, from ancient Hindu cosmology to the oscillating universe theories of the 20th century, but earlier models lacked a mechanism to avoid the singularity or to explain why the cycles should begin again. Loop quantum cosmology offers a precise mathematical mechanism that naturally resolves the singularity and drives the bounce. Moreover, loop quantum cosmology makes testable predictions. For instance, it suggests that quantum corrections to the equations governing the early universe might leave subtle imprints in the cosmic microwave background. These might appear as specific deviations from the standard inflationary predictions, perhaps in the form of anomalies in temperature fluctuations or in the spectrum of primordial gravitational waves. While current data is not yet precise enough to confirm or refute these predictions, future observations, particularly of B-mode polarization in the microwave background, could offer important clues. Another fascinating consequence of loop quantum cosmology is its suggestion that time itself may be emergent and reversible at fundamental scales. In classical general relativity, the arrow of time points in one direction, from lower entropy to higher entropy, from past to future. But in the quantum regime near the bounce, this arrow may blur. Time may be symmetric, meaning that the contracting and expanding phases of the universe mirror each other, at least at the level of fundamental equations. However, not all physicists agree on how to interpret this symmetry. Some propose that the pre-bounce phase was a mirror image of our own universe, evolving backward in time. Others suggest it may have been entirely different, with its own arrow of time, physical laws, or cosmological constants. These remain open questions, the answers to which could reshape our understanding of cosmological history. Despite the progress of loop quantum cosmology, it is still a developing field. Its predictions are mathematically consistent, but the challenge lies in connecting them to empirical data. Measuring the Planck scale structure of space-time directly is beyond current technology. Still, the hope is that indirect signatures, traces left in the earliest light of the cosmos, could serve as fingerprints of a bouncing universe. One strength of loop quantum cosmology is its minimalism. Unlike string theory, it does not require extra dimensions, supersymmetry, or a vast landscape of vacua. It builds directly on the known principles of quantum mechanics and general relativity, applying them in a non-perturbative way that respects background independence. This simplicity has earned it a devoted community of researchers who see it as a promising route to quantum gravity. Yet, like all models of the early universe, it faces conceptual and technical challenges. For example, the details of how quantum fluctuations evolve through the bounce, or how entropy behaves across cycles, are still being worked out. Additionally, it remains unclear whether the bounce could produce conditions suitable for inflation, or whether inflation is even necessary in this framework. Still, the bounce model changes the narrative in a fundamental way. It offers an alternative to the traditional beginning, one that preserves causality, continuity, and the laws of physics. It removes the metaphysical weight placed on the moment of creation, replacing it with a physical process embedded in a larger cosmic timeline. If the bounce is real, then nothing before the Big Bang gives way to something very real, a previous universe, governed by the same principles that shape our own. The mystery shifts not to why there is something rather than nothing, but to why the universe is structured in such a way that it bounces instead of collapsing, why it cycles rather than ends. Loop quantum cosmology thus provides a powerful counterpoint to models that treat the Big Bang as an absolute beginning. It reframes the origin question not as a point of emergence from nothingness, but as a moment of transition, part of a universe that may be far older, deeper, and more rhythmic than we imagined. While loop quantum cosmology suggests that the Big Bang might be a bounce, connecting a prior universe to our own, another, even more expansive framework proposes that the Big Bang might be the result of interactions in a much higher dimensional space. This is the domain of string theory, a mathematical attempt to unify all the fundamental forces of nature, including gravity, within a single, consistent quantum theory. And with it comes a radical reimagining of both nothingness and the origin of our universe. String theory emerged in the latter half of the 20th century, originally as an effort to describe the strong nuclear force. But its potential grew rapidly once physicists realized that the vibrations of strings could represent not just particles, but entire families of fields, including the graviton, the hypothetical quantum particle of gravity. Unlike point particles in traditional physics, strings are one-dimensional objects vibrating at specific frequencies. Each vibration mode corresponds to a different particle with its own mass and force characteristics. But string theory does not operate comfortably in the four familiar dimensions of space-time. For mathematical consistency, it requires additional dimensions, usually 10 in the most basic version, or 11 in more advanced formulations such as M-theory. These extra dimensions are not large or directly observable. Instead, they are compactified, curled up so tightly that they evade detection at ordinary energy scales. The geometry and topology of these extra dimensions play a crucial role. Depending on how they are configured, they determine the physical laws of the lower dimensional universe we observe. This leads to an enormous number of possible configurations, collectively referred to as the string landscape, each corresponding to a different set of physical constants and laws. From this landscape arises a bold cosmological idea: brane cosmology. In this view, our universe is not the totality of existence, but a three-dimensional surface, called a brane, floating within a higher dimensional space known as the bulk. This is sometimes compared to a two-dimensional sheet of paper embedded in three-dimensional space. Just as creatures living on the paper would be unaware of the dimension above them, we might be unaware of the additional dimensions in which our universe is embedded. In this context, the Big Bang might not have been the beginning of time, but rather a localized event, such as a collision between two branes. When branes collide in the bulk, the energy released in the impact could create a hot, dense state that mimics the conditions of the early universe. As the branes separate again, they leave behind a universe filled with radiation, matter, and expanding space-time. This is the core idea behind the ekpyrotic or cyclic universe models, developed by physicists including Justin Curry, Bert Overett, Paul Steinhardt, and Neil Turok in the early 2000s. In these models, the universe undergoes repeated cycles of contraction and expansion, with each cycle initiated by a brane collision. Unlike loop quantum cosmology, where the bounce is caused by quantum gravitational effects within four-dimensional spacetime, here the bounce occurs because of dynamics in the higher dimensional bulk. Time does not begin with the Big Bang. It continues across cycles, possibly infinitely into the past and future. The ekpyrotic model, named after an ancient Greek word meaning conflagration or out of fire, attempts to solve several problems in standard cosmology. Like inflation, it explains the flatness and uniformity of the universe, but it does so without requiring an early burst of exponential expansion. Instead, the smoothing effect comes from the slow contraction that occurs before the brane collision, ironing out irregularities before the next Big Bang-like event. Moreover, these models offer a new interpretation of nothing. In string theory, empty space is not truly empty. It is a structured entity defined by fields, branes, and topology. Even the vacuum state has multiple configurations, each with its own physical properties. Transitions between these states can occur via quantum tunneling or thermal fluctuations. What appears to us as nothing may actually be a metastable vacuum, a temporary phase in a much richer and more complex energy landscape. One implication of this is that the Big Bang could be a phase transition rather than a creation event. Just as water freezes into ice or boils into vapor, the universe might shift from one vacuum state to another. In some scenarios, this transition is catalyzed by the collision of branes. In others, it might happen spontaneously through quantum tunneling across the string landscape. Either way, the birth of a universe does not require absolute nothingness, just the right configuration of fields in a higher dimensional space. Physicists like Gabriele Veneziano, one of the early pioneers of string theory, have explored pre-Big Bang cosmology, in which the universe existed in a cold, empty, and contracting phase long before it became hot and expanding. In this model, derived from the symmetries of string theory, time stretches infinitely into the past. The Big Bang is not the origin, but a high-energy event marking the transition from one phase of the universe's evolution to another. This approach has some advantages. It avoids the need for a singular beginning, provides a framework for understanding cosmic initial conditions, and embeds cosmology in a broader, high-dimensional structure. But it also faces challenges. Modeling the physics of brane collisions is mathematically difficult, and translating predictions into observable consequences remains an ongoing task. One area of promise lies in gravitational wave astronomy. The collision of branes or transitions between vacuum states might leave detectable signatures in the form of primordial gravitational waves, ripples in spacetime generated in the earliest moments of the universe. These waves would carry information about events before the Big Bang, encoded in their frequency spectrum and polarization patterns. Future observatories, both ground-based and space-based, may be able to test these ideas by searching for such signatures. Another line of investigation focuses on cosmic strings, one-dimensional defects that may form in the early universe, predicted by some string theory models. If detected, these objects would offer direct evidence of physics beyond the standard model, possibly linked to the structure of higher dimensions. Critics of string cosmology often point to its lack of direct experimental support. Despite its mathematical elegance and unifying ambition, string theory has yet to make clear, unique predictions that can be tested in the laboratory. Its vast landscape of possible universes, while conceptually intriguing, can also seem like a retreat from falsifiability. Nonetheless, proponents argue that the theory's internal consistency and its ability to absorb both quantum mechanics and general relativity make it a worthy candidate for exploring the ultimate questions of existence. At the very least, string cosmology expands our sense of what is possible. It invites us to imagine that our universe is not all there is, that we may be living on a brane in a much larger cosmos, surrounded by other branes and fields, invisible but real. In this picture, the Big Bang is no longer a singularity or a beginning, but a transition from one geometric configuration to another, from one vacuum state to the next, perhaps part of a cycle with no beginning and no end. In this redefined framework, nothing becomes even more elusive. It is not an empty space, nor a moment before time. It is the absence of our particular configuration, The silence before the vibration, the flatness before the geometry folds, the stillness before a brain trembles. And yet, even in that absence, the rules of string theory still hold. The potential for creation still exists, embedded in the fabric of higher dimensional reality, from the ancient void of early philosophy to the dynamic landscape of modern string theory. The question of nothingness has taken us across centuries and dimensions. But even here, the mystery continues. Could the information encoded in our universe, its particles, its laws, its history, be written not in the fabric of space, but on its surface? As string theory expanded our vision of the cosmos to include extra dimensions, vibrating brains, and pre-Big Bang geometries, it also gave rise to one of the most surprising and far-reaching ideas in modern theoretical physics, the holographic principle. Emerging initially from the study of black holes, the holographic principle proposes that the deepest truths about space, time, and gravity may not reside within the volume of space itself, but rather on its boundaries. It suggests that the three-dimensional world we inhabit could, in some profound sense, be a projection of information encoded on a lower dimensional surface. In this view, what we think of as nothing may be something far more subtle, an absence not of substance, but of encoded information. This bold idea was born from a paradox. In the 1970s, physicists were attempting to reconcile the behavior of black holes with the laws of quantum mechanics. Black holes, according to general relativity, are regions of space-time where gravity becomes so intense that nothing, not even light, can escape. They are bounded by a surface known as the event horizon, beyond which information about matter falling in is lost to the outside world. Stephen Hawking, applying quantum field theory to curved space-time, made the astonishing discovery that black holes are not entirely black. Instead, they emit radiation due to quantum effects near the event horizon, a phenomenon now known as Hawking radiation. Over immense periods of time, this radiation causes the black hole to shrink and eventually evaporate. But this led to a troubling puzzle. If a black hole evaporates completely, what happens to the information about the matter that fell into it? Quantum mechanics insists that information is never truly lost. Every quantum process, however complex, must be reversible in principle. But Hawking's calculations implied that the information was destroyed, violating this foundational rule. This became known as the black hole information paradox. Trying to resolve this paradox, physicists began rethinking the nature of information and gravity. In the mid-1990s, Dutch physicist Gerard 't Hooft and American physicist Leonard Susskind proposed a radical solution. All the information contained within a volume of space might actually be stored on its boundary surface, just as a hologram encodes a three-dimensional image on a two-dimensional film. This became the holographic principle, a conjecture that the maximum amount of information that can be contained in a region of space is proportional not to its volume, but to its surface area. The principle was not just metaphorical, it was deeply mathematical. In fact, the entropy of a black hole, the measure of information or disorder, is proportional to the area of its event horizon, not its volume. This was first discovered by Jacob Bekenstein, who showed that black hole entropy scales with the surface area in units of Planck length squared. Later, this principle found a more concrete mathematical realization in the form of the ADAS-CFT correspondence, developed by physicist Juan Maldacena in the late 1990s. In this model, a gravitational theory in a curved space with negative curvature, called anti-de Sitter space, is equivalent to a quantum field theory without gravity defined on the boundary of that space. The bulk physics, including space-time and gravity, is fully captured by a lower dimensional, non-gravitational system on the edge. While our universe is not an anti-de Sitter space, the ADS-CFT correspondence gave strong evidence that gravity and quantum mechanics are not only compatible, but might be two sides of the same coin, each describing the same phenomena from a different perspective. It provided a powerful example of how space, time, and gravity could emerge from more fundamental quantum degrees of freedom. Applied to cosmology, the holographic principle offers a profound rethinking of the early universe. If the entirety of the universe's structure can be described by information encoded on a boundary, then perhaps the origin of our cosmos, what we think of as the Big Bang, was not a burst of matter and energy into space, but the unfolding of information already encoded on a primordial surface. In this sense, the universe may not have been created in the conventional way. Instead, it might be the result of information becoming activated, an entropic transition from a low information state to a higher one. The emergence of time itself could correspond to the progressive unfolding of correlations between bits of information. This perspective changes how we might define nothing. In traditional terms, nothing is the absence of matter, energy, space, and time. But if space-time itself is emergent, if it arises from underlying quantum information, then nothingness may correspond to a state of no information, or to a state in which information exists but is maximally compressed and unstructured. In such a state, there are no distinguishable particles, no dimensions, and no motion, because these require distinctions, separations, and relationships, all of which depend on the existence of structured information. When that information becomes accessible, when patterns and correlations arise, spacetime, particles, and causality emerge as effective descriptions. This idea is supported by studies of quantum entanglement, where correlations between distant particles suggest that the structure of space itself may be knitted together by entanglement. In some theoretical models, spacetime geometry can be derived from the pattern of entanglement in an underlying quantum system. The more entangled the system, the more robust and connected the emergent space becomes. This leads to a powerful insight. Space and time might not be fundamental ingredients of the universe. Instead, they are emergent properties, like temperature or pressure, that arise only when many quantum systems interact in particular ways. Before the Big Bang, then, could mean before entanglement, before correlation, before information was organized in a way that allows space-time to exist. Some physicists have taken this even further. Theorists like Mark van Ramsdonk have argued that entanglement is not merely part of spacetime, it is spacetime. The connectivity we experience as geometry could be the result of how information is shared across quantum systems. In this view, the Big Bang may be reinterpreted as a phase transition in the informational substrate of the cosmos, a jump from disconnected, unstructured quantum elements to a smooth, coherent spacetime fabric. If that is the case, then the beginning of the universe is not a singular point in time, but a transition from formless quantum potential to structured spacetime reality. It is the point at which information becomes ordered enough to define distances, durations, and interactions. And if the structure of spacetime is ultimately determined by the flow of information, then black holes, quantum fluctuations, and the vacuum itself are all part of the same informational system. What we perceive as emptiness may be filled with latent structure, waiting to be activated. Nothing becomes a placeholder for the unmanifest, a state of zero entanglement, zero complexity, or maximal symmetry. Even time may be an emergent illusion. In holographic models, the flow of time can correspond to the renormalization of quantum systems, a kind of computational unfolding of increasingly complex structures. The passage of time, then, is not something that happens in the universe, but something that emerges with the universe as its informational content grows. What does this mean for the question that has guided this entire exploration? How did nothing exist before the Big Bang? In the holographic view, before may not be a meaningful term. The universe did not emerge in time. Time emerged with the universe. And nothing may not be an absence, but a state with no accessible or usable information, a kind of informational vacuum from which all structure arises. In the traditional sense, nothing referred to a lack of substance. But modern physics suggests that what we call nothing may instead be the foundational source of all things, a state where the rules of emergence, not the rules of matter, determine what comes next. As we approach the final chapters of this journey, we find ourselves standing on the edge of knowledge itself. The idea that everything, space, time, matter, energy, emerges from information stored on a surface challenges everything we thought we knew about the fabric of reality. It also changes how we think about origins. The beginning may not be a moment, it may be a transformation. Having followed the scientific journey through quantum fields, cosmological inflation, bounces, brains, and holographic horizons, we now find ourselves in territory where physics begins to dissolve into something deeper and more abstract. philosophy, not because physics has failed, but because the questions it has raised reach beyond its formal boundaries. As we continue to ask, what came before the Big Bang? Or how can something emerge from nothing? We inevitably collide with problems of language, logic, and definition. To move forward, we must examine not just the universe, but how we think and speak about it. The idea of nothing has a long and complex history in philosophical thought. Across cultures and centuries, thinkers have wrestled with the concept of absence, non-being, and void, not only in physical terms, but in metaphysical and logical ones. Is nothing an actual state that can exist? Or is it merely a conceptual placeholder, a way for humans to talk about what is not yet or what no longer is? At first glance, the question may seem absurd. How can nothing be anything? As the pre-Socratic philosopher Parmenides argued in ancient Greece, what is not is not. He concluded that to think about nothing is already to treat it as something, violating its very nature. In his view, reality must be a full, unchanging unity. Change, becoming, and especially coming from nothing, were illusions. But not all philosophers agreed. A generation later, Democritus and Leucippus, the first atomists, argued that motion and change required the existence of the void, a kind of nothing that allows atoms to move. Without emptiness between things, nothing could change, and nothing could exist apart from a solid block of being. This was the beginning of a conceptual distinction that would endure. The difference between absolute nothingness and relative emptiness. In medieval thought, especially within Christian theology, the notion of creation, ex nihilo, creation from nothing, became central. The idea was not just that the universe had a beginning, but that it was brought into being by a transcendent cause, namely God, without pre-existing matter. This stood in contrast to earlier views where gods might shape the world from chaos or primordial material. The theological nothing was not a vacuum or absence within space and time. It was the total absence of space, time, substance, and law, a state of metaphysical non-being. But what exactly does it mean to create from nothing? Can such a thing even be intelligible? 20th century philosopher Martin Heidegger famously asked, "Why is there something rather than nothing?" A question he considered the most fundamental of all. For Heidegger, this question revealed not just a metaphysical puzzle, but an existential one. Human beings are uniquely capable of questioning being itself, and in doing so, they encounter nothing, not as a void to be feared, but as the ground for all understanding of existence. In analytic philosophy, this tension was further explored through language and logic. Bertrand Russell, for example, criticized the misuse of nothing as a noun. When people say nothing exists, they often speak as though nothing were a thing with its own properties. But this, Russell argued, is a category error. Nothing is not a referent, it is a negation. It means not anything. To treat it as a kind of substance is to misuse language. Similarly, philosopher David Albert, in his review of Lawrence Krauss's A Universe from Nothing, argued that much of the confusion stems from ambiguity in how physicists and philosophers define nothing. When physicists talk about the universe arising from nothing, they often mean from a quantum vacuum or a low-energy field state, a configuration that still obeys laws, contains fields, and assumes space-time structure. But for philosophers, nothing means nothing at all. No fields, no time, no laws, no potentiality. Albert's critique is not anti-scientific. It is a call for conceptual clarity. If we wish to claim that science explains how the universe came from nothing, we must be precise about what nothing entails. Is it a vacuum, a minimal field, a lawless state, or truly the absence of all existence? If we do not define our terms, we risk speaking past each other. Some thinkers go further still, arguing that nothing cannot be coherently conceived. Derek Parfit, a leading moral and metaphysical philosopher, suggested that rather than asking why the universe exists, we might instead ask why this universe rather than another. He explored the space of possible realities, not just physical ones, but logical structures, moral frameworks, and mathematical truths. In Parfit's view, even nothing is just one option among many, and perhaps, paradoxically, it is the least natural. This leads to an inversion of the original question. Instead of asking, why is there something rather than nothing, we might ask, why would we expect there to be nothing at all? If existence in all its forms is fertile, diverse, and abundant, then nothingness may be not the default, but the rarest of possibilities, so unstable that it cannot last. Modern cosmology echoes this intuition. Whether through inflation, quantum tunneling, brain collisions, or holographic emergence, the consistent theme is that the vacuum is active, the void is structured, and the nothing of physics is pregnant with possibility. If laws of nature exist at all, then spontaneous transitions, fluctuations, and instantiations of structure become not just possible, but probable. Still, a lingering discomfort remains. Can science ever truly explain the origin of existence without begging the question? Can a theory account for its own conditions of validity? If every law or mechanism requires a prior structure in which it operates, then the regress may never end. We either accept an ultimate brute fact, a reality that simply is, or we enter the realm of metaphysics, where explanations are no longer scientific but philosophical. Physicist and philosopher Sean Carroll addresses this tension directly. He argues that it is not the job of science to explain why there is something rather than nothing. Rather, science seeks to describe the patterns and regularities in what exists. The question of ultimate origin may be ill-posed or beyond current empirical reach, but this does not diminish science's power. It means that some questions are not about data or equations, but about the framework in which such tools are meaningful. This is why some thinkers, both scientists and philosophers, believe we must learn to live with mystery, not as a failure of reason, but as a recognition of our cognitive limits. Our minds evolved to model a world of objects, events, and causes, not timeless quantum geometries or pre-space-time information surfaces. When we ask about nothing, we are projecting our intuitions into a domain where they may not apply, and yet we ask anyway. We continue to ask, not because we expect an answer that satisfies all curiosity, but because the question itself defines us, the desire to know what came before, what lies behind, and what is not. This is the root of both philosophy and science. In the end, the question of nothing may be less about physics or metaphysics and more about meaning. What matters is not just whether the universe came from nothing, but what we make of that possibility. If everything we know and are emerged from a state with no classical structure, no time, and no matter, then perhaps our deepest truths lie not in the things we see, but in the transitions, the thresholds, the moments where definition breaks down and something new begins. This is where science and philosophy meet, not to offer final answers, but to deepen the question. And in doing so, they bring us back to ourselves, the creatures who wonder, who question, and who live always on the edge of what can be known. While philosophy invites us to reflect on the conceptual boundaries of existence, science remains committed to pushing against those boundaries with evidence. And though the origin of the universe, especially if it came from nothing, may seem forever out of experimental reach, physicists are not content to leave the question purely to theory. Across the globe, in deep underground laboratories, high-altitude observatories, particle accelerators, and orbiting satellites, researchers are searching for subtle traces, cosmic clues that may reveal what happened in the earliest fractions of a second after the universe began. In doing so, they are attempting to peer past the veil of the observable cosmos and reconstruct what came before. The most fruitful tool for this endeavor has long been the cosmic microwave background, or CMB. This faint afterglow of the Big Bang was first detected in the mid-20th century, as previously discussed, and has since become one of the cornerstones of observational cosmology. The CMB offers a snapshot of the universe approximately 380,000 years after its birth, when photons decoupled from matter and began traveling freely through space. But modern technology has allowed scientists to look beyond this surface, not by observing earlier light, since there was none before the CMB, but by analyzing the tiny fluctuations within the CMB itself. These fluctuations, which appear as temperature differences on the order of 1 part in 100,000, encode information about the initial density variations that would eventually give rise to galaxies, clusters, and large-scale structures. Experiments such as COBE, WMAP, and Planck have mapped these fluctuations with increasing precision. Each new mission has revealed more about the geometry, composition, and age of the universe, but perhaps most importantly, they have helped constrain models of the early universe, including theories of inflation, quantum origin, and multiverse dynamics. In the subtle statistical patterns of the CMB, physicists search for signs of non-Gaussianity, anisotropies, or unusual correlations that might hint at phenomena beyond the standard Big Bang picture. One of the most exciting avenues of inquiry involves the search for primordial gravitational waves. These are not the gravitational waves detected by LIGO and Virgo. Those originate from events like black hole mergers in the relatively recent cosmos. Primordial gravitational waves, by contrast, would have been generated during inflation itself, caused by rapid fluctuations in the fabric of spacetime. These waves could leave a telltale signature in the polarization pattern of the CMB, known as B-mode polarization. Detecting this signal would be a major breakthrough. It would provide not only confirmation of inflation, but also a window into the energy scale at which it occurred. That, in turn, would help discriminate between different models of quantum cosmology and perhaps constrain how, or whether, the universe could have emerged from a quantum vacuum or a no-boundary state. To find such a signal, scientists have launched and are planning a series of highly sensitive experiments. Ground-based observatories like BICEP, SPT-Pol, and Simon's Observatory, as well as proposed space missions like LightBird, aim to push the limits of CMB polarization measurements. These instruments must contend with foreground contamination from galactic dust and synchrotron radiation, but progress continues steadily. Another experimental frontier lies in particle physics, particularly in the search for phenomena beyond the standard model. While the Large Hadron Collider at CERN confirmed the existence of the Higgs boson, it has not yet uncovered direct evidence for supersymmetry, extra dimensions, or dark matter particles, all of which are predicted by theories that also inform early universe cosmology. However, particle accelerators can still offer critical insights. By recreating conditions that mirror those of the early universe, albeit at lower energies, scientists can test how particles behave at high temperatures and densities. These experiments help refine theoretical models of phase transitions, symmetry breaking, and vacuum structure, which in turn influence our understanding of what nothing might be in a physical sense. At the same time, underground detectors such as Xenon-T, Lux Zeppelin, and Pandax are hunting for dark matter, an invisible substance that makes up the bulk of matter in the universe but has never been directly observed. Some theories suggest that dark matter might be a relic from an earlier phase of the universe, or even a remnant of processes that occurred near or before the Big Bang. Finding it would not only reshape cosmology, but also provide new tools for probing the nature of the vacuum. Another angle of investigation is the quest for topological defects, cosmic relics, like cosmic strings, domain walls, or magnetic monopoles. These structures are predicted by some grand unified theories and string theory variants, and they may have formed during symmetry-breaking phase transitions in the very early universe. If they exist, they could leave observational traces in gravitational wave backgrounds, or in distortions in the CMB. The discovery of such relics would be extraordinary. It would indicate that the early universe passed through phases very different from what we now observe, possibly offering insights into pre-Big Bang conditions. In certain models, cosmic strings could even provide evidence for higher dimensional brane interactions or support the idea of a cyclic or bouncing universe. Then there are attempts to test quantum gravity, the still elusive theory that would unify quantum mechanics with general relativity. Though we lack a complete formulation, candidate theories like loop quantum gravity and string theory offer testable features. Some propose that spacetime may have a granular or discrete structure at the Planck scale, which could manifest as tiny violations of Lorentz invariance or anomalies in high-energy cosmic ray behavior. While these effects are extraordinarily difficult to detect, future experiments may provide relevant constraints. Observatories that study gamma-ray bursts, neutrino fluxes, or ultra-high-energy cosmic rays may one day observe hints of quantum gravitational effects, helping to bridge the gap between theory and data. Importantly, researchers are not just looking for confirmation, they are also seeking disconfirmation. Many cosmological theories predict slightly different patterns or signatures. Ruling out certain models can be as informative as supporting others. For instance, If future CMB observations continue to find no trace of B-mode polarization at the predicted level, certain inflationary models may need to be revised or discarded. Beyond observational data, new techniques in data analysis, machine learning, and computational modeling are allowing cosmologists to test a wider range of scenarios than ever before. High-resolution simulations of the early universe can now incorporate quantum fluctuations, field interactions, and topological effects with increasing accuracy, helping scientists explore how small differences in initial conditions might lead to dramatically different cosmic outcomes. In many ways, the current era of cosmology resembles a detective story. The clues are faint and scattered, hidden in patterns of light, ripples in space-time, and the rarest particle interactions. But piece by piece, the picture sharpens. Even if we cannot directly witness the universe emerging from nothing, we can search for the echoes it may have left behind, the patterns and probabilities that speak of an origin deeper than time itself. This process does not guarantee final answers. Some mysteries may remain permanently outside our empirical reach. Yet the search itself is meaningful. It transforms vague speculation into rigorous investigation. It forces theories to confront data. It grounds metaphysical questions in physical reality. And so, science continues to probe the earliest moments, not only to understand how the universe began, but to discover what kind of questions are possible. Because in searching for traces of nothing, we are also searching for the limits of everything, for the edge of knowledge, and perhaps for its next beginning. Despite the incredible advances in observational astronomy, theoretical physics, and experimental technology, there comes a point in any inquiry where we must ask, are there boundaries to what science can tell us? Not just temporary boundaries, caused by lack of data or limited instruments, but fundamental limits rooted in the structure of nature itself, or in the human mind's capacity to understand it. As we approach the question of how something can arise from nothing, these limits come into focus more sharply than ever. Throughout this documentary, we have followed the unfolding story of the universe's origin, from ancient philosophical debates to general relativity to quantum field theory, inflation, string theory, and beyond. Each theoretical framework has taken us one step closer to describing the conditions of the early universe, and perhaps even the moment of its emergence. But each has also revealed new layers of uncertainty, new questions that seem to retreat just as they come into view. One such limit is mathematical in nature. In the early 20th century, Austrian logician Kurt Gödel proved that within any consistent formal mathematical system, powerful enough to describe arithmetic, there are true statements that cannot be proven within that system. This result, known as Gödel's incompleteness theorem, implies that no formal system can fully explain itself from within. There will always be truths that cannot be derived from the rules alone. When applied to physics, Gödel's insight becomes more than a mathematical curiosity. It suggests that any complete theory of everything, if such a thing exists, may still contain elements that are true but unprovable, aspects of the universe that cannot be deduced from first principles. Some physicists interpret this as a soft ceiling on our ability to produce a final self-contained theory of the cosmos. A second boundary arises from quantum uncertainty. As established by Werner Heisenberg, quantum systems are inherently probabilistic. One cannot simultaneously know a particle's exact position and momentum, nor can one predict the precise outcome of any quantum event. The wave function only provides probabilities. This indeterminacy is not due to instrument failure, but is baked into the nature of quantum systems. If the origin of the universe was a quantum event, as many models now suggest, then perhaps we can never know precisely why this universe emerged, as opposed to another, or none at all. The best we may achieve is a probability distribution over possible outcomes. The actual history we observe might be just one draw from a cosmic lottery. From a philosophical point of view, this undermines the idea of a singular deterministic cause for existence. Yet another boundary comes from cosmic horizons. Because the universe is expanding, and because the speed of light is finite, there are regions of the universe we can never observe, no matter how long we wait or how advanced our telescopes become. The cosmic event horizon defines the edge of our observable universe. Beyond it, events may occur that are causally disconnected from us forever. This has implications for multiverse models, eternal inflation, and string landscapes. If other bubble universes lie beyond our causal horizon, then by definition they are untestable. We can infer their existence from theoretical models, but we cannot observe them directly. This places such ideas on the fringe of empirical science. Interesting, plausible, but ultimately non-falsifiable by current standards. Some physicists, like Sabine Hossenfelder, have raised concerns about this shift toward models that resist direct testing. When theories become so flexible or speculative that no experiment can confirm or refute them, are we still doing science? Or have we crossed into metaphysics dressed in mathematical clothing? Others, like Max Tegmark, embrace the idea that mathematics itself is the ultimate reality and that even unobservable structures can be considered real if they are mathematically consistent. In this view, the universe is not merely described by math, it is math. From this perspective, the question of why anything exists is replaced by a landscape in which everything that can exist mathematically does. Our universe is simply one such structure. These ideas test not only the limits of observation, but also the boundaries of explanation. As philosopher of science Nancy Cartwright points out, scientific models are often not literal truths, but useful fictions, idealized constructions that help us make predictions and organize data. When models become disconnected from observable reality, they may still be beautiful, internally consistent, and mathematically rich, but their epistemic status becomes murky. Are they discoveries or inventions? Then there are limits of language and cognition. The human brain evolved not to understand quantum tunneling or curved space-time, but to survive on the savannah. Our categories, cause, effect, substance, space, time, are deeply rooted in this evolutionary history. When we ask what happened before time or what existed outside space, we may be applying the wrong tools to the problem. Our questions could be malformed from the start. As Carlo Rovelli, a theoretical physicist and philosopher, notes, perhaps the ultimate insight is not what we discover about the universe, but what we discover about ourselves. Physics may one day describe a universe with no beginning, or one that loops endlessly, or one that emerges from quantum rules without reference to space and time. But our ability to conceptualize such a universe, to represent it in thought or language, may never fully catch up. This does not mean we should abandon the search. On the contrary, science thrives on confronting the unknown. The recognition of limits is itself a form of progress. It helps refine the questions we ask. It encourages humility in the face of complexity, and it preserves the integrity of science by reminding us that not all questions are equally tractable. Moreover, the practical reach of science continues to grow. The same tools developed to study the early universe, particle accelerators, radio telescopes, gravitational wave detectors, also drive advances in technology, medicine, and engineering. In probing the limits of the cosmos, we also expand the boundaries of what it means to be human. So, what might remain forever beyond our reach? We may never know with certainty whether the universe began from true nothingness or from a quantum vacuum that itself has no origin. We may never be able to distinguish between a universe created by a unique event and one that emerged from an infinite sea of possibilities. We may never observe other universes or recover the lost information swallowed by black holes. But perhaps that is not a failure. Perhaps the goal of science is not to solve every mystery, but to clarify it, to map the terrain of the unknown, even if some regions remain in shadow. The search for cosmic origins, then, becomes a journey not to a final answer, but to a deeper understanding of what it means to ask. As we approach the final stage of this exploration, we return to the question that started it all. How did nothing exist before the Big Bang? We have seen that nothing is not a simple void, but a concept that changes with context. Philosophical, mathematical, physical, quantum, and informational. We have seen that the boundary between nothing and something may not be sharp, and that the birth of the universe may not be an absolute beginning, but a transformation from one state to another. After traveling through the deepest theories of physics, the farthest reaches of cosmology, and the most abstract frontiers of philosophy, we return to the question that launched this journey. How did nothing exist before the Big Bang? Along the way, we have seen that this question is not simple, and neither is its answer. It is not just a scientific inquiry, but a philosophical, linguistic, and existential one. And now, at the edge of our exploration, we may not have a final answer, but we have gained something more powerful, a clearer understanding of what is being asked. In our modern scientific framework, nothing is no longer understood as a blank void. Rather, it is context-dependent. In classical physics, a vacuum was empty space, a region without matter, but still part of the stage on which events played out. In quantum field theory, that vacuum became alive with fluctuations, virtual particles, and probabilistic energy exchanges. In cosmology, the vacuum could inflate, collapse, or tunnel into existence, driven by quantum laws we are only beginning to understand. And in string theory and holography, nothing becomes the absence of encoded information, or a transition point between distinct configurations of geometry and field. Each perspective redefines the boundaries between something and nothing. At no point did we find a firm, singular state that could unambiguously be called absolute nothing. Instead, we encountered a rich spectrum of not yet, states with no classical space or time, but with rules, symmetries, and potential. Whether through quantum bounces, tunneling events, brain collisions, or smooth no-boundary transitions, the story of the universe's beginning became not a moment of creation from true void, but a transformation within a framework that allows for emergence. This does not render the concept of nothing meaningless. Rather, it teaches us that our intuitions about nothingness, drawn from human-scale experience, may not apply at cosmic or quantum scales. When we imagine nothing, we picture emptiness, absence, silence, but nature appears to be fundamentally dynamic. Even in what we consider empty space, there is structure and lawfulness. Perhaps nothingness, in its purest form, has never existed. Or perhaps it is so unstable, so fleeting, that it instantly gives rise to something, because it cannot be otherwise. This leads to a deeper insight. The universe may not have needed an external cause or a creator in the traditional sense. The laws of physics, if they exist outside of space and time, could themselves be sufficient. If they allow for the spontaneous emergence of a quantum universe, governed by probabilities and capable of self-organization, then nothing is not the absence of cause, but the condition for possibility. And yet, even as science builds these extraordinary models, it remains grounded in humility. We now understand that some questions may always lie beyond observation, shielded by horizons or buried beneath quantum uncertainty. We may never directly witness the birth of space or time, but that does not make the question meaningless. It makes it precious. The fact that we can even pose such a question and seek its answer through mathematics, measurement, and reflection is a testament to human curiosity, a trait as fundamental to us as the laws we study. In this documentary, we have moved from ancient philosophers debating the void, to Newton's absolute space, to Einstein's curved spacetime. We have watched the universe expand through Hubble's observations and inflate through Guth's theory. We have considered whether the Big Bang was a singularity or a bounce, a boundary or a transition. We have explored the landscape of multiverses, the geometry of brains, and the informational architecture of holography. And we have listened to philosophers remind us that words like nothing are not always as clear as they seem. Through it all, one theme has emerged: emergence itself. The universe may not have a beginning in the conventional sense, but a process of becoming, a transition from one state to another, driven not by miracles, but by structure. And that structure may not require preconditions we can define in spatial or temporal terms. It may simply be. This does not mean we are at the end of the story. In fact, we may be at its beginning. With each new telescope, particle detector, and theoretical insight, our ability to test and refine these models grows. In the coming decades, we may detect gravitational wave imprints from the earliest instance of cosmic inflation. We may uncover the true nature of dark matter or discover patterns in the cosmic microwave background that hint at a pre-Big Bang geometry. We may even learn how to unify quantum mechanics with gravity, unlocking the final mathematical key to the nature of time and space. But we must also be prepared for the possibility that the ultimate question, why is there something rather than nothing, will remain open, not because it is unsolvable, but because it is perhaps the wrong kind of question for science alone to answer. It may belong not to the realm of experiments or equations, but to the human need for meaning, story, and context. In that sense, the mystery of nothing is not a flaw in our knowledge. It is a reflection of our desire to know what lies behind all knowing. And that brings us, full circle, to the paradox with which we began. How can nothing exist before the Big Bang? Perhaps it did not. Perhaps the universe is eternal in some form, or perhaps time itself began with the bang, making the question moot. Perhaps before is a misapplied term. Or perhaps at the foundation of it all is a state not of nothingness, but of pure potential, a condition from which existence naturally arises, not through intention, but through necessity. In any case, what we do know is this: from this profound question has grown a profound science, a science that has illuminated the sky, unraveled atoms, and connected the vast and the minute. A science that continues to evolve, not only in what it discovers, but in how it defines the questions worth asking. We began by asking how nothing might have existed. We end with a deeper understanding of everything. And between the two lies the story of the cosmos and the remarkable human endeavor to comprehend it.